On October 9th, 2022, something happened in space that broke physics detectors across the solar system. Satellites went blind. Ground-based instruments overloaded. The International Space Station's radiation monitors spiked so dramatically that mission control initially feared a malfunction. But this wasn't equipment failure. This was something far more extraordinary. Tonight, let yourself drift into the story of cosmic events so powerful they challenge our fundamental understanding of reality itself. Settle in, forget about time, and let's explore the phenomena that have forced scientists to question everything they thought they knew about the universe. The event that shattered instruments across the solar system lasted exactly 7 minutes and 12 seconds. In that brief span, a single cosmic explosion released more energy than our sun will produce over its entire 10 billion year lifetime. The explosion occurred 2.4 billion light-years away, yet its effects were felt throughout our solar system as if a cosmic bomb had detonated in our immediate neighborhood. Gamma-ray bursts represent the most violent events in the known universe, but the October 2022 burst was different. Astronomers had never recorded anything like it. The burst, designated GRB 221009A, earned an unofficial nickname among researchers, the BOAT, or brightest of all time. The name wasn't chosen lightly. In the 6 decades since gamma-ray astronomy began, scientists had detected thousands of these cosmic explosions. None came close to the raw power of what happened that October morning. The story of gamma-ray bursts begins not with cosmic explosions, but with Cold War paranoia and the ever-present fear of nuclear annihilation. In the 1960s, the United States military launched a series of satellites called Vela, designed to monitor the atmosphere for signs of secret nuclear weapons testing. The satellites carried gamma-ray detectors capable of identifying the unique radiation signature of nuclear explosions from orbit. On July 2nd, 1967, the Vela satellites detected something unexpected. A burst of gamma rays had indeed triggered their detectors, but the signal came from space, not Earth. The burst exhibited characteristics that no nuclear weapon could produce. The radiation arrived from a direction above the Earth's atmosphere, and its intensity pattern differed markedly from any known terrestrial source. For years, this detection remained classified. Military officials worried that acknowledging the discovery might reveal the capabilities of their surveillance satellites. Meanwhile, scientists who had access to the data struggled to understand what they had observed. The gamma rays were far more energetic than anything known to exist in space, and they appeared to come from random directions rather than from any identifiable astronomical object. The breakthrough came in 1973 when Ray Klebesadel and his colleagues at Los Alamos National Laboratory published the first scientific paper describing these mysterious cosmic flashes. They had analyzed data from 16 separate events detected by multiple Vela satellites between 1969 and 1972. The paper's title was deceptively modest: Observations of Gamma-ray Bursts of Cosmic Origin. The implications were anything but modest. Klebesadel's team had discovered that the universe routinely produces explosions of unimaginable violence. The gamma rays in these bursts carried energies millions of times greater than visible light. Even more perplexing, the bursts appeared to come from everywhere and nowhere. Unlike stars, planets, or galaxies, gamma-ray bursts showed no preference for particular regions of sky. They seemed to pop off randomly across the celestial sphere, as if the entire universe was sporadically detonating. The randomness of gamma-ray burst directions created a fundamental puzzle for astronomers. If these explosions occurred within our galaxy, they should cluster toward the galactic plane where most stars reside. Instead, they appeared uniformly distributed across the sky. This suggested either that gamma-ray bursts occurred in a spherical halo surrounding our galaxy, or that they were so distant they effectively surrounded us at cosmological distances. The distance question dominated gamma-ray burst research for decades. Were these explosions happening in our cosmic backyard, perhaps in the outer reaches of the Milky Way? Or were they occurring in distant galaxies, billions of light years away? The answer would determine whether gamma-ray bursts were relatively modest local phenomena or the most powerful explosions in the universe. The debate intensified throughout the 1980s and early 1990s as new satellites detected hundreds of additional bursts. Each detection added to the mystery rather than solving it. Some bursts lasted milliseconds, others continued for minutes. Some produced smooth, gradually declining light curves, while others flickered chaotically with multiple peaks and valleys. The diversity of gamma-ray burst properties seemed to defy any simple explanation. The resolution came in 1997 with an observation that transformed our understanding of cosmic violence. On February 28th, the BeppoX satellite detected GRB 970228, a gamma-ray burst that appeared unremarkable during its initial few seconds of emission. What made this burst extraordinary was what happened next. Within hours of the gamma-ray detection, BeppoX's X-ray cameras had pinpointed the burst's location with unprecedented precision. For the first time, astronomers knew exactly where in the sky a gamma-ray burst had occurred. Ground-based telescopes quickly turned to the location and made a discovery that settled the distance debate forever. The burst site showed a fading afterglow of optical light, gradually dimming over several days. But more importantly, the afterglow lay within a distant galaxy whose redshift indicated a distance of approximately 8 billion light-years. GRB 970228 had originated in a galaxy so far away that its light had been traveling toward Earth since long before our solar system formed. The distance measurement had staggering implications for the energy scale of gamma-ray bursts. If GRB 970228 occurred 8 billion light-years away, yet still appeared bright to Earth-based detectors, the explosion must have released energy equivalent to converting several solar masses directly into gamma rays. No known physical process could account for such extreme energy release. The discovery that gamma-ray bursts were cosmological phenomena rather than local events immediately elevated them to the status of the most luminous electromagnetic events in the universe. A typical gamma-ray burst releases more energy in 10 seconds than our galaxy's 100 billion stars produce in an entire year. The most energetic bursts approach the theoretical limit for electromagnetic explosions, releasing energies comparable to the rest mass of our sun converted entirely to radiation. The energy requirements for gamma-ray bursts pushed theoretical astrophysics to its limits. Only the most extreme cosmic events could generate such enormous energy releases. The leading candidates included the gravitational collapse of massive stars into black holes, the collision of neutron stars, or perhaps even the evaporation of primordial black holes formed in the early universe. As more gamma-ray bursts were detected and localized, patterns began to emerge in their properties and host galaxy environments. Bursts lasting longer than 2 seconds typically occurred in galaxies with active star formation, suggesting a connection to massive, short-lived stars. Shorter bursts showed no such preference, appearing in both young and old galactic environments. The pattern pointed toward two distinct populations of gamma-ray burst sources. Long-duration bursts seemed to be associated with the deaths of massive stars, while short bursts might result from different processes altogether. This dual nature added complexity to an already mysterious phenomenon. The massive star connection gained support through the detection of supernovae following some long-duration gamma-ray bursts. These observations suggested that gamma-ray bursts might represent hypernova explosions, where the core collapse of extremely massive stars produces not only a supernova, but also a highly collimated jet of relativistic particles. The hypernova model provided a plausible mechanism for the extreme energies observed in gamma-ray bursts. When a massive star's core collapses to form a black hole, the infalling matter can generate powerful magnetic fields and rotation that focus energy into narrow jets. If Earth happens to lie along the jet direction, we observe a gamma-ray burst. If not, we might only see a supernova explosion. This beaming model helped resolve the energy crisis that had plagued gamma-ray burst theory. If the energy release was concentrated into narrow cones rather than radiated isotropically, the total energy requirement could be reduced by factors of hundreds or thousands. A gamma-ray burst might represent only a tiny fraction of a hypernova's total energy output, focused into a beam that we observe from a favorable viewing angle. However, even with beaming corrections, gamma-ray bursts remained extraordinarily energetic events. The most powerful bursts still required energy releases comparable to the complete annihilation of several Earth masses. Such extreme energies pushed the boundaries of what stellar collapse models could reasonably produce. The theoretical challenges intensified with the discovery of ultra-long duration gamma-ray bursts that defied classification in either the short or long categories. These events continued producing gamma rays for thousands of seconds, far longer than any stellar collapse model could sustain. Some ultra-long bursts showed evidence for multiple energy injection episodes, as if their central engines had somehow restarted after periods of quiescence. GRB 111209A, detected on December 9, 2011, exemplified the ultra-long category with a duration exceeding 25,000 seconds. The burst's energy output remained roughly constant for over 7 hours, requiring a central engine capable of sustained operation far beyond what any known stellar process could maintain. The event challenged fundamental assumptions about gamma-ray burst physics and progenitor models. The host galaxy of GRB 111209A provided additional puzzles. The galaxy showed signs of recent star formation, consistent with a massive star progenitor, but the required stellar mass to power such a long-duration burst exceeded any known stellar population. The event seemed to require a progenitor star more massive than stellar evolution models could realistically produce. Meanwhile, short-duration gamma-ray bursts were revealing their own secrets through increasingly precise localizations and follow-up observations. The host galaxies of short bursts showed markedly different properties from long burst hosts, with older stellar populations and lower star formation rates. These environments suggested progenitors with longer evolutionary timescales than massive stars. The neutron-star merger model for short gamma-ray bursts gained support through theoretical calculations and observational evidence. When two neutron stars spiral together and merge, the resulting collision can produce conditions similar to those in stellar core collapse, including the formation of a black hole surrounded by an accretion disk. The process naturally explains both the energy requirements and host galaxy properties of short bursts. The neutron-star merger model received dramatic confirmation on August 17, 2017, when gravitational wave detectors observed the merger of two neutron stars in a galaxy 130 million light-years away. Just 1.7 seconds after the gravitational wave signal ended, gamma-ray satellites detected a short-duration burst from the same sky location. The coincidence provided direct evidence linking neutron-star mergers to gamma-ray burst production. The gravitational wave detection, designated GW170817, opened a new chapter in gamma-ray burst research by enabling multi-messenger astronomy. For the first time, scientists could study a cosmic explosion through gravitational waves, electromagnetic radiation, and eventually neutrinos. The wealth of information available from this single event exceeded what decades of previous gamma-ray burst research had provided. The optical counterpart of GW170817 displayed properties that matched theoretical predictions for kilonovae, explosions powered by the radioactive decay of heavy elements formed through rapid neutron capture in neutron-rich environments. The observation confirmed that neutron star mergers serve as cosmic factories for gold, platinum, and other heavy elements, while simultaneously producing gamma-ray bursts. However, the gamma-ray burst associated with GW170817 was surprisingly weak compared to typical short bursts detected at similar distances. The discrepancy suggested that either the burst was viewed from an unfavorable angle or that neutron star mergers produce a wide range of gamma-ray burst brightnesses depending on specific merger conditions. The viewing angle interpretation gained support through detailed modeling of the burst's afterglow emission. The data suggested that the gamma-ray burst jet was indeed present but pointed away from Earth, so that only the edges of the emission cone were visible. This off-axis viewing explained both the weak gamma-ray emission and the unusual properties of the afterglow light curve. The success of the off-axis jet model for GW 170817 implied that many gamma-ray bursts might go undetected because their jets are pointed away from Earth. The true rate of neutron star mergers, and presumably short gamma-ray bursts, could be much higher than apparent detection rates suggest. This realization had important implications for understanding the cosmic production rate of heavy elements and the contribution of mergers to gravitational wave backgrounds. As gamma-ray burst research matured, attention turned to the most extreme events that challenged theoretical understanding. These outliers pushed the boundaries of known physics and forced scientists to consider exotic possibilities that conventional models could not accommodate. GRB 080319b, detected on March 19, 2008, became famous as the gamma-ray burst visible to the naked eye. Despite occurring 7.5 billion light-years away, the burst briefly reached a visual magnitude of 5.8, making it temporarily brighter than any star in the night sky except for our Sun. No astronomical object had ever been observed at such a combination of distance and brightness. The naked eye visibility of GRB 080319b required extreme fine-tuning of the burst's properties and viewing geometry. The explosion had to be both intrinsically luminous and precisely aligned with Earth's line of sight to achieve such remarkable brightness. The event represented a cosmic coincidence of extraordinary rarity. Detailed analysis of GRB 080319b revealed evidence for multiple emission components with different physical origins. The prompt gamma-ray emission showed the typical characteristics of internal shocks within a relativistic jet, while the optical flash appeared to originate from the jet's interaction with surrounding material. The complexity of the emission mechanisms highlighted the intricate physics operating within gamma-ray burst sources. The optical brightness of GRB 080319b also enabled unprecedented studies of the burst's host galaxy environment. Spectroscopic observations revealed that the explosion occurred in a region of active star formation, consistent with a massive star progenitor, but the immediate environment showed unusual chemical properties that suggested recent interactions with neighboring stars or stellar winds. Another extreme event, GRB 130427a, detected on April 27, 2013, produced the highest energy gamma rays ever recorded from a cosmic explosion. The burst generated photons with energies exceeding 95 billion electron volts, roughly 20 billion times more energetic than visible light. These ultra-high energy gamma rays pushed the theoretical limits for particle acceleration in astrophysical environments. The production of such energetic photons required magnetic fields and shock velocities at the extreme end of what relativistic jet models could accommodate. The acceleration mechanisms needed to produce 95 billion electron-volt photons approached the theoretical maximum efficiency for converting kinetic energy into electromagnetic radiation through known physical processes. GRB 130427a also exhibited unusual temporal behavior, with high-energy gamma-ray emission continuing for hours after the initial burst. This extended emission suggested that the central engine remained active long after the prompt explosion, continuing to inject energy into the relativistic jet. The sustained activity challenged models that predicted rapid jet termination following stellar core collapse. The combination of extreme energies and extended duration in GRB 130427a pointed toward progenitor scenarios involving the most massive stars possible within stellar evolution constraints. The required stellar mass approached the theoretical limit for stars that can maintain hydrostatic equilibrium without collapsing to black holes during their main sequence evolution. As gamma-ray burst catalogs grew to include thousands of events, statistical studies revealed population properties that individual burst observations could not provide. The distribution of burst energies, durations, and spectral properties painted a picture of cosmic explosion physics operating under a wide range of extreme conditions. The energy distribution of gamma-ray bursts follows a power law extending over several orders of magnitude, with the most energetic events being exponentially rarer than moderate energy bursts. This distribution suggests that the underlying physical processes operate near critical thresholds, where small variations in initial conditions can produce dramatically different outcomes. The redshift distribution of gamma-ray bursts extends to some of the highest values known for any astronomical objects, with several bursts detected from galaxies that existed when the universe was less than 10% of its current age. These high redshift bursts provide unique probes of star formation and stellar evolution in the early universe. GRB 090423, detected on April 23, 2009, held the record for the most distant gamma-ray burst with a redshift of 8.2, corresponding to a light travel time of 13.035 billion years. The burst occurred when the universe was only 630 million years old, during the epoch when the first generations of massive stars were forming and dying. The detection of gamma-ray bursts at such early cosmic epochs implies that massive star formation and death occurred much sooner after the Big Bang than many models predicted. The first stars in the universe, formed from primordial hydrogen and helium, could grow to enormous masses in the absence of metals that normally limit stellar growth through cooling processes. These population 3 stars, as they are known, could achieve masses hundreds of times greater than our Sun before becoming unstable and collapsing to black holes. Their deaths through hypernova explosions would produce gamma-ray bursts with unprecedented energies, while simultaneously enriching the early universe with the first heavy elements. The study of high redshift gamma-ray bursts has provided crucial insights into the reionization epoch, when the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen that filled the universe. Gamma-ray burst afterglows serve as background light sources that probe the ionization state of intervening gas clouds. These cosmological applications of gamma-ray burst research have elevated the field beyond pure astrophysics into fundamental cosmology. Gamma-ray bursts now serve as tools for studying dark energy, measuring cosmic expansion rates, and understanding the formation of the first celestial objects. The precision required for these cosmological applications has driven technological advances in gamma-ray detection and rapid follow-up observations. Modern gamma-ray burst satellites can localize events to arc-minute precision within seconds of detection, enabling ground-based telescopes to begin afterglow observations before the optical emission peaks. The SWIFT satellite, launched in 2004, revolutionized gamma-ray burst research through its ability to autonomously detect bursts and rapidly repoint its X-ray and optical telescopes to the burst location. SWIFT's rapid response capabilities enabled the discovery of afterglow emission from hundreds of gamma-ray bursts, providing distance measurements and host galaxy identifications. The Fermi Gamma-Ray Space Telescope, operational since 2008, extended gamma-ray burst studies to higher energies than previously accessible. Fermi's Large Area Telescope can detect gamma rays with energies up to hundreds of billions of electron volts, revealing the most extreme particle acceleration processes operating in gamma-ray burst jets. Fermi's observations have shown that many gamma-ray bursts produce high-energy emission that continues long after the prompt burst phase ends. This extended high-energy emission provides insights into the jet's interaction with surrounding material and the efficiency of particle acceleration in relativistic shock environments. Ground-based gravitational wave detectors have opened new possibilities for multi-messenger studies of gamma-ray bursts, particularly those associated with neutron star mergers. the advanced LIGO and Virgo detectors can sense gravitational waves from mergers throughout a volume of space containing millions of galaxies. The joint detection of gravitational waves and gamma-ray bursts provides complementary information about the merger process and subsequent explosion. Gravitational waves probe the final seconds of the inspiral and merger, while electromagnetic observations reveal the longer-term evolution of material ejected during the collision. Future gravitational wave detectors will have sufficient sensitivity to detect neutron star mergers at cosmological distances, potentially observing hundreds of merger-associated gamma-ray bursts per year. This flood of multi-messenger detections will transform our understanding of cosmic explosions and their role in cosmic chemical evolution. The next generation of gamma-ray burst missions promises to extend observations to even higher energies and larger sky coverage. The Cherenkov Telescope Array, currently under construction, will observe gamma-ray bursts at energies approaching 1 trillion electron volts, probing particle acceleration mechanisms operating at the absolute limits of known physics. These future observations may finally resolve long-standing puzzles about gamma-ray burst physics, such as the nature of the central engine, the composition of relativistic jets, and the maximum possible energy release from stellar explosions. The answers to these questions will impact our understanding of stellar evolution, black hole formation, and the limits of physics under extreme conditions. The study of gamma-ray bursts has also revealed unexpected connections to other areas of astrophysics and fundamental physics. The extreme magnetic fields required for some gamma-ray burst models approach the quantum electrodynamic limit, where vacuum itself becomes unstable and spontaneously produces particle-antiparticle pairs. These quantum electrodynamic effects could influence the propagation of high-energy gamma rays through the strong magnetic fields near gamma-ray burst sources. Photon-photon interactions in such environments might produce observable signatures that could test quantum field theory under conditions impossible to replicate in terrestrial laboratories. The polarization properties of gamma-ray burst emission provide additional probes of extreme physics operating in relativistic jets. Linear polarization measurements can reveal the magnetic field structure within the jet, while circular polarization might indicate exotic processes involving parity violation or magnetized plasma effects. Early polarization measurements of gamma-ray bursts have yielded conflicting results, with some events showing high polarization levels, while others appear essentially unpolarized. The diversity of polarization properties suggests that jet magnetic field configurations vary significantly between different burst sources or evolution phases. The search for neutrino emission from gamma-ray bursts has intensified with the operation of large-scale neutrino detectors, such as IceCube in Antarctica. High-energy protons accelerated in gamma-ray burst jets should interact with ambient photons to produce neutrinos, providing an independent probe of the acceleration mechanism. Despite extensive searches, no confirmed neutrino detections have been associated with gamma-ray bursts. The lack of neutrino signals places constraints on the proton content of relativistic jets and the efficiency of hadronic acceleration processes. These limits suggest that gamma-ray burst jets may be dominated by electron-positron pairs rather than protons. The absence of strong neutrino signals from gamma-ray bursts has implications for their contribution to the flux of ultra-high energy cosmic rays observed at Earth. If gamma-ray bursts cannot efficiently accelerate protons to ultra-high energies, alternative sources must be responsible for the most energetic cosmic ray particles. Meanwhile, the cosmic ray connection has motivated searches for delayed high-energy emission from gamma-ray burst locations. Ultra-high energy cosmic rays accelerated in gamma-ray burst jets would interact with the cosmic microwave background radiation during their journey to Earth, producing secondary particles that might be detectable. The time delays between gamma-ray burst detection and cosmic ray arrival could span years to decades, depending on the burst distance and cosmic ray energy. These delayed signatures would provide unique tests of cosmic ray acceleration models and propagation physics over cosmological distances. The environmental impact of gamma-ray bursts on their host galaxies has become an active area of research as observations reveal the detailed structure of burst surroundings. The intense radiation from a nearby gamma-ray burst could sterilize planets within hundreds of light years, affecting the development of life in galactic regions. Mass extinction events in Earth's history have been tentatively linked to gamma-ray bursts occurring within our galaxy or nearby galaxies. The Ordovician extinction 450 million years ago coincided with evidence for increased cosmic ray bombardment that might have resulted from a galactic gamma-ray burst. However, the frequency of gamma-ray bursts in galaxies like the Milky Way appears too low to account for regular mass extinctions. Statistical analyses suggest that dangerous gamma-ray bursts might occur in our galaxy only once every few hundred million years, making them unlikely causes of the periodic extinction events observed in the fossil record. The rarity of nearby gamma-ray bursts has implications for the development of complex life in the universe. Galaxies with higher star formation rates and more massive star populations would experience more frequent gamma-ray bursts, potentially preventing the evolution of advanced life forms through repeated sterilization events. This connection between gamma-ray bursts and astrobiology has motivated studies of gamma-ray burst rates in different types of galaxies and cosmic epochs. The peak of cosmic star formation occurred when the universe was roughly one-third its current age, corresponding to a period of enhanced gamma-ray burst activity. The high gamma-ray burst rate during this epoch might have delayed the development of complex life throughout the universe, with habitable conditions becoming common only after star formation rates declined and gamma-ray burst frequencies decreased to safer levels. These astrobiological considerations have influenced discussions about the Fermi paradox and the apparent absence of detectable extraterrestrial civilizations. If gamma-ray bursts have repeatedly sterilized promising biospheres throughout cosmic history, the rarity of advanced life might reflect these episodic catastrophes rather than fundamental constraints on biological evolution. The search for gamma-ray burst afterglows in archival images has revealed orphan afterglows, transient sources that brighten and fade with the characteristic signature of gamma-ray burst jets, but without detected prompt gamma-ray emission. These orphan events might represent gamma-ray bursts viewed from unfavorable angles where the jet emission cone points away from Earth. The discovery of orphan afterglows suggests that the true rate of gamma-ray burst explosions significantly exceeds the observed detection rate. If gamma-ray burst jets are narrowly collimated, most events would appear as orphan afterglows rather than prompt gamma-ray detections. This geometric selection effect has important implications for understanding the cosmic rate of stellar core collapse and neutron star formation. The total rate of failed supernovae that produce black holes without optical explosions might be much higher than previously estimated based on gamma-ray burst observations alone. The failed supernova connection has motivated searches for direct collapse events where massive stars form black holes without producing detectable explosions. These events would appear as disappearing stars in deep imaging surveys, leaving behind only the newly formed black holes. Several candidate disappearing star events have been identified in nearby galaxies, but confirming their nature requires long-term monitoring to verify that the stars have indeed vanished rather than simply dimmed temporarily. The rarity of these events makes statistical studies challenging with current observational capabilities. The connection between gamma-ray bursts and stellar evolution has also revealed unexpected diversity in the final stages of massive star death. Some massive stars appear to undergo multiple episodes of instability before final collapse, producing supernova imposter events that might precede eventual gamma-ray burst production. These complex evolutionary pathways suggest that the relationship between stellar mass and final fate is more nuanced than simple theoretical models predict. Environmental factors such as metallicity, rotation, and binary interactions can dramatically alter the evolution of massive stars and their ultimate explosions. The role of stellar rotation in gamma-ray burst production has received particular attention, as observations reveal that burst progenitors must be rapidly rotating to generate the necessary magnetic field configurations. The angular momentum requirements approach the theoretical limits for stellar rotation before centrifugal forces overcome gravitational binding. Achieving such extreme rotation rates requires special circumstances during stellar evolution, possibly involving mass transfer from binary companions or magnetic field interactions that can spin up stellar cores. The rarity of these conditions might explain why gamma-ray bursts represent only a small fraction of massive star deaths. Binary evolution models for gamma-ray burst progenitors involve complex interactions between stellar winds, mass transfer, and tidal forces that can dramatically alter the evolution of both stars. The final stellar structure and rotation rate depend sensitively on the binary separation, mass ratio, and timing of various evolutionary phases. Some binary scenarios produce merged stars with extremely rapid rotation and complex internal structure that might be conducive to gamma-ray burst production. These models naturally explain the rarity of gamma-ray bursts while providing mechanisms for achieving the necessary rotation rates and magnetic field configurations. The observational verification of binary evolution models requires identifying the signatures of past binary interactions in gamma-ray burst host environments. Chemical abundance patterns, stellar population characteristics, and spatial distributions of burst locations within host galaxies provide clues about progenitor evolution histories. Recent studies have found evidence for enhanced nitrogen abundances in the vicinity of some gamma-ray burst locations, possibly indicating Wolf-Rayet star evolution that strips away hydrogen and helium layers to reveal nuclear processed material. These abundance patterns support models involving massive star progenitors with complex evolutionary histories. The host galaxy properties of gamma-ray bursts continue to provide constraints on progenitor models and selection effects. Long-duration bursts show strong preferences for low metallicity, actively star-forming galaxies, while short bursts appear in a wider range of galactic environments. The metallicity dependence of long gamma-ray bursts suggests that stellar evolution in metal-poor environments favors the production of rapidly rotating massive stars. Lower metallicity reduces the efficiency of stellar winds, allowing stars to retain more angular momentum throughout their evolution. This metallicity effect has implications for the cosmic evolution of gamma-ray burst rates. During early cosmic epochs, when galaxy metallicities were universally low, gamma-ray burst production might have been much more efficient than in the present-day universe. The enhanced gamma-ray burst rate in the early universe has consequences for cosmic reionization and the formation of the first galaxies. The intense radiation from frequent gamma-ray bursts could have contributed to ionizing the neutral hydrogen that filled intergalactic space after the cosmic dark ages. These cosmological effects of gamma-ray bursts add another layer to their significance beyond pure astrophysics. The explosions that challenge our understanding of stellar death also played important roles in shaping the large-scale structure and ionization history of the universe. The theoretical modeling of gamma-ray burst jets has advanced significantly through numerical simulations that can follow the complex interactions between relativistic outflows and stellar envelopes. These simulations reveal the detailed mechanisms by which stellar core collapse can produce highly collimated relativistic jets. The key insight from numerical modeling is that jet formation requires specific configurations of magnetic fields and rotation that can focus the explosion energy into narrow cones. The efficiency of this focusing process determines whether a core collapse event produces a gamma-ray burst or a more conventional supernova explosion. The simulations also reveal that jet propagation through stellar envelopes involves complex shock interactions that can modify the jet properties and create the conditions for gamma-ray production. The details of these processes depend sensitively on the stellar structure and composition, explaining the diversity of observed gamma-ray burst properties. Advanced simulations have begun to include the effects of magnetic field evolution and neutrino interactions that can influence jet formation and propagation. These additional physics components are crucial for understanding the most extreme events that push the boundaries of stellar explosion physics. The computational requirements for realistic gamma-ray burst simulations have driven developments in high-performance computing and parallel processing algorithms. The multi-scale nature of the problem, spanning from nuclear physics in stellar cores to relativistic jet propagation over stellar dimensions, challenges current computational capabilities. Future simulations will incorporate increasingly sophisticated treatments of magnetic field generation, neutrino transport, and nuclear physics that govern the equation of state in ultra-dense matter. These advances will enable more accurate predictions of gamma-ray burst properties and rates. The observational requirements for testing theoretical models continue to drive technological advances in gamma-ray detection and multi-wavelength follow-up capabilities. The next generation of gamma-ray missions will provide improved sensitivity, better localization, and broader energy coverage than current facilities. The gamma-ray burst investigation via polarimetry and spectroscopy mission, scheduled for launch in the mid-2020s, will measure the polarization properties of gamma-ray burst emission for the first time with sufficient precision to constrain jet magnetic field configurations. These measurements will provide crucial tests of theoretical models. Ground-based telescopes are also advancing rapidly, with extremely large telescopes capable of detecting afterglow emission from gamma-ray bursts at unprecedented distances. The James Webb Space Telescope has already begun observing gamma-ray burst afterglows in the infrared, revealing host galaxy properties at higher redshifts than previously accessible. The synergy between space-based gamma-ray detection and ground-based follow-up observations continues to drive discoveries about the most extreme cosmic explosions. Each new detection provides additional pieces to the puzzle of how nature produces such extraordinary displays of cosmic violence. The field of gamma-ray burst research has evolved from a curiosity discovered through military satellites to a major area of astrophysics that touches on fundamental questions about stellar evolution, cosmology, and the limits of physics under extreme conditions. The events that once seemed impossible are now recognized as crucial laboratories for understanding the universe. Yet for all the progress made over 5 decades of research, gamma-ray bursts continue to surprise scientists with new phenomena that challenge theoretical understanding. The October 2022 event that broke detectors across the solar system represents just the latest in a series of discoveries that force scientists to expand their conception of what nature can accomplish. The cosmic explosions that keep scientists awake at night, poring over data and revising theories, serve as reminders that the universe operates on scales of violence and energy that dwarf human experience. In their brief, brilliant flashes, gamma-ray bursts reveal physics operating at the absolute extremes of what natural processes can produce. Somewhere in the cosmos, another massive star is approaching the end of its life, its core growing ever denser as nuclear fuel runs out. In a few moments of cosmic time, that star will collapse, perhaps producing a jet of relativistic particles that will announce its death to the universe with a burst of gamma rays. If that jet happens to point toward Earth, our instruments will record another chapter in the ongoing story of cosmic violence. The signals from these distant catastrophes continue their billion-year journeys across space, carrying information about physics under conditions we can barely imagine. The scientists who dedicate their careers to understanding these events are the modern descendants of ancient stargazers, using the most sophisticated technology humanity has ever created to decode messages from the most violent corners of the universe. In the endless dialogue between humanity and the cosmos, gamma-ray bursts represent some of the most dramatic cosmic utterances we have learned to interpret. Each detection brings new insights into the fundamental processes that govern stellar death, black hole formation, and the limits of physics under extreme conditions. The universe continues to broadcast its secrets through these spectacular explosions, and humanity continues to listen, driven by an insatiable curiosity about the magnificent and terrifying complexity of the cosmos we inhabit. The human cost of gamma-ray burst research often goes unrecognized behind the spectacular science and theoretical breakthroughs. The field demands a peculiar form of scientific stamina where researchers must remain perpetually ready for the next cosmic catastrophe. Unlike conventional astronomy, where observations can be planned months in advance, gamma-ray burst science operates on the universe's schedule, not humanity's. Dr. Neil Gehrels, who led NASA's Swift mission until his passing in 2017, once described the lifestyle of gamma-ray burst researchers as resembling that of emergency room physicians. The comparison was apt. When a burst triggers satellite detectors, researchers around the world receive automated alerts regardless of the hour. A significant detection at 3 a.m. triggers a cascade of activity as radio telescopes swing toward the burst location. Optical telescopes begin rapid imaging sequences, and teams of scientists interrupt their sleep to coordinate follow-up observations. The international nature of gamma-ray burst research has created a unique form of scientific collaboration driven by the transient nature of afterglow emission. When NASA's Swift satellite detects a burst from its orbit above North America, the information immediately flows to observatories across 6 continents. The European Southern Observatory's telescopes in Chile might begin observations, while the Very Large Telescope in the Atacama Desert simultaneously starts spectroscopic measurements. Meanwhile, radio telescopes in Australia and South Africa add their data to the growing picture of the cosmic explosion. This global coordination operates with the efficiency of air traffic control, but the stakes extend far beyond missed flights. Gamma-ray burst afterglows fade rapidly, often dropping below detection thresholds within hours or days of the initial explosion. Miss the critical observation window, and years might pass before a similar opportunity arises. The pressure to respond quickly has transformed gamma-ray burst astronomy into one of the most time-critical fields in all of science. The competitive aspect of gamma-ray burst research has intensified as the field has matured and the potential for breakthrough discoveries has become apparent. The race to achieve the first precise localization, to detect the most distant burst, or to identify exotic emission signatures drives researchers to push their instruments and techniques to absolute limits. This competition has accelerated scientific progress while creating tensions within what was traditionally a collaborative scientific community. The Chinese astronomical community's entry into gamma-ray burst research has added new dimensions to this international competition. The Hard X-ray Modulation Telescope, known as InSight HXMT, became operational in 2017 and immediately began contributing unique observations to the field. Chinese researchers achieved particular success in detecting the highest energy gamma rays from several bursts, revealing emission components that Western instruments had missed. The success of Chinese missions prompted other space agencies to accelerate their own gamma-ray burst programs. The European Space Agency's Integral Observatory enhanced its burst detection capabilities, while Russia's Spectre-RG mission incorporated gamma-ray burst monitoring as a secondary science objective. Japan's partnership with international collaborators on the Suzaku and ASTROH missions maintained their historical leadership in X-ray astronomy applications to burst research. The technological arms race in gamma-ray burst detection has driven innovations that extend far beyond astronomy. The real-time data processing requirements for burst detection have pushed the boundaries of computational capability, while the need for rapid telescope repointing has advanced robotic control systems. These developments have found applications in telecommunications, autonomous vehicles, and military surveillance systems. Modern gamma-ray burst satellites incorporate artificial intelligence systems that can autonomously classify bursts and prioritize follow-up observations without human intervention. The algorithms that distinguish genuine cosmic explosions from instrumental artifacts or solar particle events represent some of the most sophisticated pattern recognition software ever deployed in space. The false alarm problem that has plagued gamma-ray burst research since the Vela discoveries continues to challenge even these advanced systems. Solar flares, particle precipitation events, and spacecraft charging can all mimic the signatures of distant cosmic explosions. The 1979 Vela incident, where a suspected nuclear weapons test turned out to be either a solar particle event or a small asteroid impact, demonstrated the difficulty of distinguishing terrestrial from cosmic gamma-ray sources. More recent false alarms have provided sobering reminders of the challenges involved in gamma-ray burst verification. In 2010, the Fermi satellite detected what initially appeared to be an unusually bright burst from a nearby galaxy. Hours of intensive follow-up observations failed to find any afterglow emission, leading to the eventual conclusion that the event was a statistical fluctuation in the detector background rather than a genuine cosmic explosion. The verification protocols developed in response to such incidents now require multiple independent confirmations before burst alerts are distributed to the astronomical community. These safeguards prevent wild goose chases, but occasionally delay rapid response to genuine events. The balance between speed and accuracy remains a persistent challenge in a field where both factors are crucial for scientific success. The economic ecosystem surrounding gamma-ray burst research has grown into a substantial enterprise involving government agencies, universities, and aerospace contractors across multiple continents. NASA's gamma-ray burst program alone represents hundreds of millions of dollars in satellite development, operations, and data analysis over the past 2 decades. The European Space Agency's contributions through missions like Integral and the upcoming Athena Observatory add comparable investments. The return on these investments extends beyond immediate scientific discoveries to include technological innovations, international cooperation, and educational benefits. The technologies developed for gamma-ray burst detection have found applications in medical imaging, nuclear security, and space weather monitoring. The international collaborations fostered by burst research have strengthened diplomatic ties between participating countries while training the next generation of space scientists and engineers. Corporate involvement in gamma-ray burst research has increased as private space companies recognize the technical challenges and potential commercial applications. SpaceX has provided launch services for several gamma-ray burst missions, while companies like Ball Aerospace and Thales Alenia Space have developed specialized detectors and spacecraft subsystems. The emerging commercial space industry sees gamma-ray burst research as a testing ground for technologies that might eventually support more commercially oriented space ventures. The educational impact of gamma-ray burst research extends from elementary schools to graduate programs in astrophysics. The dramatic nature of cosmic explosions captures public imagination in ways that more mundane astronomical phenomena cannot match. Planetarium shows featuring gamma-ray bursts consistently rank among the most popular programs, while university courses on high-energy astrophysics use bursts as compelling examples of extreme physics. Graduate students entering gamma-ray burst research must master an unusually broad range of skills spanning observational astronomy, theoretical physics, and computational science. The multi-wavelength nature of burst studies requires familiarity with radio, optical, X-ray, and gamma-ray observational techniques. The rapid pace of the field demands proficiency in real-time data analysis and automated observing systems. The career paths available to gamma-ray burst researchers have diversified as the field has matured and its techniques have found broader applications. Traditional academic careers in universities and national laboratories remain important, but opportunities have expanded to include positions in aerospace companies, government research facilities, and technology startups. The data analysis and signal processing skills developed in burst research translate well to applications in finance, telecommunications, and artificial intelligence. The gender dynamics within gamma-ray burst research reflect broader patterns in physics and astronomy, where women remain underrepresented despite comprising significant portions of undergraduate student populations. Several pioneering women have made crucial contributions to the field, including Krissa Kuveliotu's work on magnetar connections and Judith Rakusan's studies of prompt optical emission. However, women continue to face barriers in career advancement and leadership roles within the field. Professional organizations have implemented programs to address these disparities, including mentorship initiatives, childcare support at conferences, and bias training for search committees. Progress has been gradual but measurable, with women comprising increasing fractions of graduate students and postdoctoral researchers in gamma-ray burst groups. The international nature of gamma-ray burst research has created unique opportunities for scientists from developing countries to participate in cutting-edge research through remote observing programs and data-sharing initiatives. Researchers in countries without major space programs can contribute to burst science through ground-based follow-up observations and theoretical modeling studies. South Africa's participation in gamma-ray burst research through the Mir-KAT radio telescope array exemplifies how emerging space science programs can make significant contributions to the field. The telescope's location in the southern hemisphere provides coverage of sky regions inaccessible to northern facilities, while its advanced digital signal processing capabilities enable novel studies of burst radio emission. Similar opportunities exist for researchers in Chile, where international observatories provide access to world-class optical and infrared telescopes. The high altitude and exceptional atmospheric conditions of the Atacama Desert make it an ideal location for studying faint gamma-ray burst afterglow. Chilean universities have developed strong graduate programs in astrophysics that train students to operate these facilities and contribute to international research collaborations. The cultural impact of gamma-ray burst discoveries extends beyond scientific circles to influence popular culture, science fiction, and philosophical discussions about humanity's place in the universe. The concept of cosmic explosions capable of sterilizing entire regions of galaxies has captured the imagination of science fiction writers and fueled speculation about existential threats to civilizations. The possibility that a nearby gamma-ray burst could threaten life on Earth has generated serious scientific studies as well as sensationalized media coverage. Researchers have calculated that a burst occurring within a few thousand light-years of Earth could deplete the ozone layer, leading to increased ultraviolet radiation and potential mass extinction. The frequency of such events in our galaxy appears low enough that they represent minimal immediate threats, but the possibility cannot be entirely dismissed. These considerations have influenced discussions about planetary defense and the resilience of technological civilization to cosmic threats. Unlike asteroid impacts or supervolcanic eruptions, gamma-ray bursts cannot be predicted or prevented through human intervention. The randomness of their occurrence and the vast distances involved make them fundamentally different from other natural hazards that humanity might eventually learn to mitigate. The search for gamma-ray burst signatures in the geological record has yielded intriguing but inconclusive results. Some researchers have proposed that the Ordovician mass extinction 450 million years ago might have resulted from a nearby burst that destroyed atmospheric ozone. The evidence includes unusual isotope ratios in rocks from that period and the selective extinction of marine organisms that would have been vulnerable to increased ultraviolet radiation. However, alternative explanations for the Ordovician extinction exist, including volcanism, climate change, and asteroid impacts. The difficulty of definitively linking ancient extinctions to cosmic events illustrates the challenges involved in connecting gamma-ray burst research to other scientific disciplines. The astrobiological implications of gamma-ray bursts have motivated studies of their effects on planetary atmospheres and the development of complex life. Simulations suggest that frequent bursts could delay or prevent the evolution of oxygen-producing organisms, while rare but intense events might reset evolutionary progress by eliminating advanced species. These studies have implications for the search for extraterrestrial intelligence and the apparent rarity of detectable technological civilizations. If gamma-ray bursts regularly sterilize potentially habitable worlds, the development of intelligence and technology might be even more improbable than other constraints suggest. The connection between gamma-ray bursts and the Fermi paradox has influenced strategies for searching for extraterrestrial signals. Some researchers have proposed that technological civilizations might develop gamma-ray burst early warning systems to protect their populations from cosmic sterilization events. The detection of such protective technologies might serve as technosignatures indicating the presence of advanced civilizations. Meanwhile, the extreme energies involved in gamma-ray bursts have attracted attention from researchers interested in fundamental physics and the possibility of new physical phenomena. The conditions near gamma-ray burst sources approach regimes where general relativity, quantum mechanics, and thermodynamics all operate simultaneously at their theoretical limits. The study of gamma-ray burst polarization has provided tests of quantum electrodynamics under conditions impossible to replicate in terrestrial laboratories. The intense magnetic fields and high-energy photon densities near burst sources can trigger quantum vacuum effects that modify the propagation of electromagnetic radiation. Attempts to detect these exotic quantum effects have pushed observational techniques to their limits. The Icaros solar sail mission carried polarimetric instruments designed to measure gamma-ray burst polarization with sufficient precision to detect quantum vacuum birefringence. While definitive detections remain elusive, the constraints achieved have provided valuable tests of theoretical predictions. The energy scales involved in gamma-ray bursts also provide opportunities to search for physics beyond the standard model of particle physics. Some theoretical models predict that high-energy photons might decay into exotic particles or interact with hypothetical fields that could be detected through their effects on burst spectra. The search for axions, hypothetical particles that could solve several problems in particle physics and cosmology, has motivated specialized studies of gamma-ray burst emission. Axions would interact weakly with photons in strong magnetic fields, potentially creating detectable modifications to burst spectra or polarization properties. Similarly, the possibility that space-time itself might have a granular structure at the Planck scale has motivated searches for dispersion effects in gamma-ray burst signals. High-energy photons might travel slightly slower than low-energy photons if space-time quantization affects electromagnetic propagation, creating measurable time delays over cosmological distances. These searches for new physics have yet to yield positive detections, but they have established some of the most stringent constraints on exotic phenomena available from any astronomical observations. The null results are scientifically valuable in their own right, helping to rule out theoretical models and guide future experimental investigations. The computational challenges involved in gamma-ray burst research have driven advances in data analysis techniques that benefit numerous other fields. The need to identify brief, rare signals in noisy data streams has motivated the development of sophisticated statistical methods and machine learning algorithms. These techniques have found applications far beyond astronomy, including financial market analysis, medical diagnostics, and environmental monitoring. The pattern recognition algorithms developed for distinguishing gamma-ray bursts from instrumental artifacts have been adapted for detecting fraudulent transactions, identifying disease signatures in medical images, and monitoring ecosystem changes from satellite data. The real-time processing requirements of gamma-ray burst research have also contributed to advances in distributed computing and cloud-based analysis systems. The need to coordinate observations across multiple time zones has driven the development of automated workflow systems that can manage complex observational campaigns without human intervention. These technological innovations have supported the growth of big data applications across multiple scientific disciplines. Climate scientists use similar distributed processing systems to analyze global climate models, while genomics researchers apply comparable techniques to process massive DNA sequencing datasets. The international collaboration networks established for gamma-ray burst research have served as models for other large-scale scientific projects. The protocols developed for data sharing, publication coordination, and resource allocation have been adapted for use in gravitational wave astronomy, neutrino detection, and particle physics experiments. The success of these collaborative models has influenced science policy decisions about funding and organizing international research projects. Government funding agencies increasingly require evidence of international cooperation and coordination as prerequisites for supporting major scientific initiatives. The diplomatic benefits of scientific collaboration have reinforced political support for gamma-ray burst research programs. The peaceful nature of astronomical research provides opportunities for cooperation between countries that might otherwise have limited scientific interaction. Partnerships between American and Chinese researchers, European and Russian teams, and other international combinations have created lasting relationships that transcend political tensions. These international connections have proven valuable during periods of political strain, providing communication channels and shared interests that help maintain scientific cooperation even when official diplomatic relations become difficult. The universal appeal of understanding cosmic explosions transcends national boundaries and ideological differences. The long-term sustainability of gamma-ray burst research depends on continued technological advancement, international cooperation, and sustained public support for basic scientific research. The field faces challenges from budget constraints, launch failures, and the increasing complexity of modern space missions. The cost of gamma-ray burst satellites has increased dramatically as missions have become more sophisticated and capable. Early missions like BATS on the Compton Gamma Ray Observatory cost tens of millions of dollars, while modern missions like Fermi and future concepts like GRIPS involve investments of hundreds of millions or billions of dollars. These escalating costs have forced difficult choices about mission priorities and capabilities. The trade-offs between sensitivity, sky coverage, energy range, and operational lifetime require careful optimization to maximize scientific return within available budgets. Alternative approaches to traditional large satellites are being explored, including constellations of smaller spacecraft and hosted payloads on commercial platforms. These approaches might provide cost-effective ways to maintain gamma-ray burst monitoring capabilities while developing new technologies for future missions. The emergence of commercial space companies as viable partners for scientific missions has created new opportunities for reducing costs and increasing launch flexibility. Companies like SpaceX, Blue Origin, and others have demonstrated capabilities that were previously available only from government space agencies. However, the commercial space industry also introduces new uncertainties and dependencies that must be carefully managed. The failure of commercial providers or changes in business priorities could disrupt planned missions and research programs. The development of reusable launch vehicles promises to reduce the cost of accessing space, potentially enabling more frequent gamma-ray burst missions and larger satellite constellations. The reduced launch costs might make it economically feasible to replace failed satellites quickly, rather than designing missions for extremely long operational lifetimes. These technological trends suggest that gamma-ray burst research might transition from relying on a few expensive, long-duration missions to operating multiple smaller, shorter-lived satellites that can be upgraded more frequently as technology advances. The scientific benefits of this approach include more rapid technology refresh cycles, reduced risk from single-point failures, and increased opportunities for international participation through smaller, more affordable missions. The data archiving and preservation challenges for gamma-ray burst research have grown as missions generate increasingly large volumes of information. Modern satellites can produce terabytes of data daily, creating storage and processing requirements that strain available computational resources. The long-term preservation of gamma-ray burst data requires careful attention to data formats, storage media, and access protocols. Unlike biological specimens or physical samples, digital astronomical data can become inaccessible due to obsolete file formats or failed storage systems. International standards for gamma-ray burst data archives have been developed to ensure compatibility between different missions and research groups. These standards specify data formats, metadata requirements, and access protocols that enable researchers to combine observations from multiple sources. The success of these standardization efforts has enabled meta-analyses of gamma-ray burst populations that would be impossible with incompatible data formats. researchers can now combine decades of observations from different missions to study statistical properties and evolutionary trends. Cloud computing platforms have begun to play important roles in gamma-ray burst data analysis, providing scalable computational resources and collaborative analysis environments. These platforms enable researchers without access to large computational facilities to perform sophisticated analyses using shared resources. The democratization of data analysis capabilities has broadened participation in gamma-ray burst research while reducing barriers for researchers in developing countries or smaller institutions. Students and early career scientists can contribute to cutting-edge research without requiring access to expensive computational infrastructure. The educational applications of gamma-ray burst data have expanded as online platforms make real observational data accessible to students at all levels. High school students can analyze the same data used by professional researchers, providing authentic research experiences that inspire interest in science and technology careers. These educational programs have proven particularly effective at engaging underrepresented groups in science, including women and minorities who might not otherwise consider careers in astrophysics. The combination of cutting-edge technology, international collaboration, and dramatic cosmic phenomena appeals to diverse student populations. University partnerships with gamma-ray burst missions provide opportunities for undergraduate and graduate students to work directly with space-based instruments and contribute to active research programs. These experiences often prove transformative for students who gain first-hand understanding of how modern astronomical research operates. The mentorship networks that develop through these programs create lasting connections between students and established researchers. Many current leaders in gamma-ray burst research trace their initial involvement to undergraduate experiences with space missions or data analysis projects. The quality assurance protocols for gamma-ray burst research have evolved to address the challenges of managing large international collaborations while maintaining scientific rigor. The rapid pace of discovery and the need for quick publication to establish priority have created tensions with traditional peer review processes. Specialized journals and publication tracks have been developed to handle time-critical gamma-ray burst discoveries while maintaining appropriate scientific standards. These expedited review processes enable rapid dissemination of important results while preserving the quality control functions of peer review. The development of preprint servers and online collaboration platforms has transformed how gamma-ray burst researchers share preliminary results and coordinate follow-up observations. These platforms enable real-time collaboration during rapidly evolving observational campaigns. However, the speed of modern communication has also created challenges for maintaining scientific accuracy and preventing the spread of preliminary or incorrect results. The balance between rapid communication and careful verification remains an ongoing challenge for the field. Professional societies and international organizations have developed guidelines for responsible conduct of gamma-ray burst research, addressing issues such as data sharing, authorship credits, and publication ethics. These guidelines help maintain scientific integrity while enabling effective collaboration. The intellectual property landscape surrounding gamma-ray burst research continues to evolve as commercial applications of research techniques become more apparent. Universities and research institutions must balance traditional academic values of open knowledge sharing with the need to protect innovations that could generate revenue for continued research support. Patent applications related to gamma-ray burst detection and analysis techniques have increased as the commercial potential of these technologies has become clearer. The signal processing algorithms, detector designs, and data analysis methods developed for astronomical research often have broader applications in defense, telecommunications, and medical imaging. Technology transfer offices at universities involved in gamma-ray burst research work to identify commercial opportunities, while preserving academic freedom and open scientific collaboration. The challenge lies in protecting intellectual property without hindering the free exchange of ideas that drives scientific progress. Some researchers have formed startup companies to commercialize technologies developed through gamma-ray burst research. These ventures often maintain close ties to academic institutions while pursuing commercial applications of astronomical technologies. The success of these technology transfer efforts provides additional justification for public investment in gamma-ray burst research by demonstrating tangible economic benefits beyond the immediate scientific returns. Government funding agencies increasingly expect documentation of broader impacts and commercial applications when evaluating research proposals. The workforce development aspects of gamma-ray burst research contribute to national competitiveness in high-technology industries. The students and postdoctoral researchers trained in gamma-ray burst groups develop skills in advanced electronics, data analysis, and project management that prove valuable in numerous technical careers. Industry partnerships with gamma-ray burst research groups provide internship opportunities and career paths for students while giving companies access to cutting-edge research techniques and newly trained personnel. These partnerships benefit both academic research programs and commercial technology development. The global nature of gamma-ray burst research creates opportunities for international exchange programs that expose students and researchers to different scientific cultures and approaches. These experiences often prove invaluable for developing the international perspective and collaborative skills needed for modern scientific careers. The diversity of backgrounds represented in gamma-ray burst research teams reflects the interdisciplinary nature of the field and the variety of skills required for success. Team members include traditional astronomers, particle physicists, electrical engineers, computer scientists, and specialists in fields ranging from detector development to statistical analysis. This diversity creates rich collaborative environments where different perspectives and expertise combine to address complex scientific problems. The interdisciplinary nature of gamma-ray burst research has contributed to its rapid progress and continued vitality. The management challenges involved in coordinating large, diverse, international research teams have driven innovations in project management and collaboration techniques. The lessons learned from successful gamma-ray burst collaborations have been applied to other large-scale scientific projects. Virtual collaboration tools developed for gamma-ray burst research have proven valuable for maintaining productivity during travel restrictions and enabling participation by researchers who cannot attend in-person meetings. The COVID-19 pandemic accelerated adoption of these tools and demonstrated their effectiveness for supporting international research collaborations. The resilience of gamma-ray burst research collaborations during the pandemic provided models for other scientific fields facing similar challenges. The existing infrastructure for remote collaboration and the international nature of the research community facilitated continued productivity despite travel and meeting restrictions. The environmental considerations associated with gamma-ray burst research include the carbon footprint of international travel for collaborations and conferences, the energy consumption of large computational facilities, and the environmental impact of spacecraft manufacturing and launch operations. Efforts to reduce the environmental impact of gamma-ray burst research include increased use of virtual meetings, optimization of computational algorithms to reduce energy consumption, and consideration of environmental factors in mission design decisions. The development of green computing practices for astronomical data analysis has broader implications for reducing the environmental impact of big data applications across multiple scientific disciplines. The energy-efficient algorithms and hardware optimizations developed for gamma-ray burst research contribute to sustainable computing practices. The location of major astronomical facilities in remote, pristine environments creates responsibilities for environmental stewardship that extend beyond immediate research objectives. Radio quiet zones and optical astronomy sites often serve as inadvertent nature preserves, where development is restricted to protect observational capabilities. These protected areas provide opportunities for collaboration between astronomers and conservation biologists to study ecosystem dynamics and monitor environmental changes. The long-term monitoring capabilities of astronomical facilities can contribute valuable data for climate research and biodiversity studies. The cultural heritage considerations at astronomical sites require careful balance between scientific objectives and respect for indigenous communities and historical sites. Many major observatories are located on lands with significant cultural importance to local populations. Successful partnerships between astronomical institutions and indigenous communities have created models for respectful collaboration that honors cultural values while enabling scientific research. These partnerships often include education and outreach programs that benefit local communities while building support for continued astronomical research. The economic impact of major astronomical facilities on local communities includes direct employment, support for local businesses, and educational opportunities. The presence of world-class scientific facilities often attracts additional technology companies and research institutions, creating economic development beyond the immediate astronomical research. Tourism associated with astronomical facilities provides additional economic benefits while offering opportunities for public education and outreach. Visitor programs at major observatories attract hundreds of thousands of people annually, generating revenue that supports both research operations and local economies. The inspiration provided by astronomical research, including gamma-ray burst studies, contributes to broader cultural and educational benefits that are difficult to quantify but clearly valuable. The sense of wonder and curiosity stimulated by cosmic discoveries enriches human culture while motivating pursuit of scientific and technical careers. The long-term legacy of gamma-ray burst research will include not only the scientific discoveries about cosmic explosions, but also the technological innovations, international partnerships, educational programs, and cultural contributions that have emerged from the field. Future historians of science will likely view the gamma-ray burst era as a period when humanity first began to understand the most extreme processes operating in the universe. The decade of the 2020s may be remembered as the time when multi-messenger astronomy matured and gravitational wave detections became routine, enabling comprehensive studies of cosmic explosions across all available observational channels. The next generation of gamma-ray burst researchers is being trained in an environment where international collaboration, technological innovation, and rapid discovery are normal aspects of scientific life. These researchers will inherit sophisticated instruments and established collaborative networks while facing new challenges that cannot yet be anticipated. The questions that will drive gamma-ray burst research in the coming decades include fundamental issues about the nature of matter under extreme conditions, the role of magnetic fields in cosmic explosions, and the connections between stellar evolution and black hole formation. The answers to these questions may require technological capabilities that do not yet exist and theoretical insights that await future discoveries. Yet the history of gamma-ray burst research suggests that the most important discoveries often come from unexpected directions, challenging established assumptions and opening new areas of investigation. The field has repeatedly surprised researchers with phenomena that were not predicted by existing theories. From the cosmological distances of bursts to their connection with gravitational wave sources, the cosmic explosions that first puzzled military satellite operators in the 1960s have evolved into one of the most active and rapidly advancing areas of modern astrophysics. The events that once seemed impossible are now recognized as crucial laboratories for understanding the universe under the most extreme conditions nature can provide. Somewhere in the cosmos, another massive star is approaching its final moments, perhaps destined to produce a gamma-ray burst that will be detected by humanity's ever-vigilant instruments. The explosion that results may challenge current theoretical understanding, reveal new physics, or provide the missing piece to long-standing puzzles about cosmic evolution. The signals from these distant catastrophes continue their billion-year journeys across space, carrying encrypted information about physics under conditions that exist nowhere else in the observable universe. The researchers who dedicate their lives to intercepting and decoding these cosmic messages remain the guardians of humanity's cosmic curiosity, the interpreters of signals from realms that stretch the limits of human comprehension. In the grand conversation between humanity and the universe, gamma-ray bursts represent some of the most dramatic and challenging cosmic communications we have learned to receive. Each detection adds another voice to the cosmic chorus, revealing new aspects of the magnificent and terrifying processes that govern stellar death and cosmic evolution. The universe continues to speak through these spectacular explosions, and humanity continues to listen with ever-improving instruments and expanding understanding, driven by an endless fascination with the cosmic violence that shapes the very fabric of reality. The precise measurements that define gamma-ray burst research reveal the extraordinary scales of energy and distance involved in these cosmic explosions. The October 2022 burst, GRB221009A, released approximately 1.0 times 10 to the 45th joules of energy in gamma rays alone, equivalent to converting 2.2 Earth's masses directly into electromagnetic radiation. This energy was released over a duration of 320 seconds, with the most intense emission occurring during the first 7 minutes and 12 seconds of the event. The burst originated from a galaxy designated SWIFTJ 1913.1 plus 1946, located at a redshift of Z equals 0.151, corresponding to a light travel time of approximately 1.9 billion years. At this distance, the gamma rays detected at Earth represented only a tiny fraction of the total energy output, which was beamed into a narrow cone with an estimated opening angle of 2 to 5 degrees. The total isotropic equivalent energy release approached 10 to the 47th joules, making GRB 221009A roughly 70 times more energetic than any previously detected gamma-ray burst. The spectral characteristics of GRB 221009A revealed gamma rays extending to unprecedented energies. The Fermi Large Area Telescope detected photons with energies exceeding 100 billion electron volts, while the HESS atmospheric Cherenkov telescopes in Namibia measured gamma rays with energies up to 13 trillion electron volts. These ultra-high energy photons arrived at Earth more than 10 hours after the initial burst, indicating extended particle acceleration in the burst's aftermath. The technical specifications of modern gamma-ray burst detection systems reflect decades of technological advancement driven by the need to capture these brief cosmic events. The Fermi Gamma Ray Space Telescope's Gamma Ray Burst Monitor consists of 12 sodium iodide detectors, covering energies from 12 to 1000 kiloelectron volts, and 2 bismuth germanate detectors, sensitive to photons from 150 kiloelectron volts to 30 megaelectron volts. The system can localize gamma-ray bursts to within 3 to 4 degrees and transmit alerts to ground-based telescopes within 11 seconds of detection. NASA's Neil Gehrels Swift Observatory carries 3 instruments specifically designed for rapid gamma-ray burst studies. The Burst Alert Telescope uses 32,768 individual cadmium-zinc telluride detector elements arranged in a coded aperture mask configuration to achieve a field of view of 1.4 steradians, roughly 1/6 of the entire sky. The instrument can detect bursts at rates up to 100 per year and autonomously repoint the spacecraft to the burst location within 75 seconds of detection. The Swift X-ray telescope employs a Wolter Y focusing optic with a focal length of 3.5 meters to achieve an angular resolution of 18 arcseconds. The detector consists of a 600 by 602 pixel charge-coupled device with individual pixel dimensions of 40 by 40 micrometers, providing a field of view of 23.6 by 23.6 arc minutes. The instrument can detect X-ray afterglow with fluxes as low as 2 × 10 to the minus 14th erg per square centimeter per second in the 0.3 to 10 kilo-electron-volt energy range. The Swift ultraviolet optical telescope incorporates a 30-centimeter Ritchie-Chrétien reflector with 6 filter wheels containing broadband and grism elements. The detector is a 2048 by 2048 pixel microchannel plate intensified charge-coupled device with quantum efficiency exceeding 10% across the 170 to 650 nanometer wavelength range. The telescope can begin observations of gamma-ray burst afterglows within 60 to 90 seconds of the initial detection. Ground-based follow-up observations of gamma-ray bursts employ some of the world's most sophisticated telescopes and detection systems. The Very Large Telescope in Chile consists of 4 8.2-meter unit telescopes and 4 1.8-meter auxiliary telescopes that can operate independently or in interferometric mode. For gamma-ray burst observations, the telescopes typically use rapid response modes that can begin imaging within 2 to 3 minutes of receiving burst alerts. The Atacama Large Millimeter Submillimeter Array has contributed unique observations of gamma-ray burst afterglows at wavelengths between 0.32 and 9.6 millimeters. ALMA's 66 antennas, including 54 12-meter dishes and 12 7-meter dishes, can achieve angular resolutions as fine as 0.1 arcseconds when operating in its most extended configuration with maximum baseline lengths of 16.2 kilometers. Radio observations of gamma-ray bursts have revealed afterglow emission that can persist for months or years after the initial explosion. The Carl G. Janssen Very Large Array in New Mexico employs 27 individual 25-meter dishes arranged in a Y-shaped configuration with maximum baseline lengths of 36.4 kilometers. The array operates across frequencies from 74 MHz to 50 GHz and can achieve angular resolutions ranging from 0.04 to 166 arcseconds depending on frequency and configuration. The statistical analysis of gamma-ray burst populations has revealed quantitative relationships between burst properties and their cosmic environments. The distribution of burst durations exhibits a clear bimodal structure with a separation boundary at approximately 2 seconds. Short duration bursts with 90 durations less than 2 seconds comprise roughly 25% of the observed population, while long-duration bursts account for the remaining 75%. The energy distribution of gamma-ray bursts follows a broken power law with different slopes above and below a characteristic energy of approximately 10 to the 52nd ergs. The distribution of peak energies in burst spectra, when corrected for cosmological effects, shows a characteristic value near 1 mega-electron-volt in the burst rest frame. This energy scale corresponds to typical photon energies expected from synchrotron emission in relativistic shocks. Redshift measurements for well-localized gamma-ray bursts extend from Z equals 0.0085 for GRB 980425, associated with the nearby supernova SN 1998 BW, to Z equals 9.4 for GRB 090429b, which occurred when the universe was only approximately 520 million years old. The median redshift for long-duration bursts is Z approximately 2.2, corresponding to a look-back time of 10.5 billion years. The rate density evolution of gamma-ray bursts tracks the cosmic star formation history with some important differences. The burst rate peaked at redshift Z approximately 1.5 to 2.0, somewhat earlier than the peak of cosmic star formation at Z approximately 2 to 3. This offset suggests that gamma-ray burst progenitors may have shorter delay times between formation and explosion than the typical massive star population. Host galaxy studies have provided detailed constraints on gamma-ray burst progenitor environments. The sample of 99 well-localized long-duration bursts studied by the Palomar Transient Factory showed host galaxy stellar masses ranging from 10 to the power 7.2 to 10 to the 11th.8 solar masses, with a median value of 10 to the power of 9.4 solar masses. The distribution of galaxy types includes 45% irregular galaxies, 31% spiral galaxies, and 24% elliptical or S0 galaxies. Metallicity measurements in gamma-ray burst host galaxies reveal a preference for low metallicity environments. The oxygen abundance, expressed as 12 plus log of O over H, ranges from 7.4 to 9.1, with a median value of 8.4. This median metallicity is approximately 0.7 dex lower than typical star-forming galaxies at similar redshifts, supporting theoretical models that predict enhanced gamma-ray burst production in metal-poor environments. The spatial distribution of gamma-ray bursts within their host galaxies shows significant offsets from galactic centers. The projected physical offset distribution follows an exponential profile with a characteristic scale length of 4.3 kiloparsecs. Approximately 15% of bursts occur more than 10 kiloparsecs from their host galaxy centers, indicating that some progenitors receive substantial velocity kicks during formation or experience significant stellar evolution timescales. Supernova associations with gamma-ray bursts have been confirmed for approximately 25% of nearby long-duration events. The prototypical case, GRB 980425/SN 1998 BIW, occurred at a distance of 38 megaparsecs, and demonstrated that at least some gamma-ray bursts originate from core collapse supernovae. The supernova component typically peaks 10 to 20 days after the gamma-ray burst and shows broad spectral features indicating expansion velocities of 20,000 to 30,000 kilometers per second. The energetics of supernova-associated gamma-ray bursts span a wide range. GRB 980425 released only 6 times 10 to the 47th ergs in gamma rays, while GRB 030329 produced 1.2 times 10 to the 52nd ergs. The kinetic energy of associated supernovae typically ranges from 10 to the 52nd power to 5 times 10 to the 52nd power ergs, comparable to or exceeding the gamma-ray energy output. Gravitational wave observations have provided direct confirmation of the neutron-star merger model for short-duration gamma-ray bursts. The event GW 170817, detected by the Advanced LIGO and Virgo interferometers on August 17, 2017, involved the merger of neutron stars with masses of 1.17 and 1.60 solar masses. The gravitational wave signal lasted 100 seconds and exhibited the characteristic chirp pattern of an inspiraling binary system. The associated gamma-ray burst, GRB 170817A, was detected 1.74 seconds after the gravitational wave signal ended by both the Fermi Gamma Ray Burst Monitor and the integral SPIA-CS detector. The burst duration was approximately 2 seconds with a total energy release of 5 times 10 to the 46th ergs, assuming isotropic emission. However, detailed modeling suggests the burst was viewed roughly 30 degrees off-axis from the jet center, implying a true jet energy of approximately 10 to the 49th power ergs. The optical counterpart, designated AT2017 GFO, was discovered 11 hours after the merger in the galaxy NGC 4993 at a distance of 40 megaparsecs. The transient showed the characteristic red color and rapid evolution expected for a kilonova powered by radioactive decay of R process elements. Spectroscopic observations revealed signatures of newly synthesized strontium, confirming theoretical predictions about heavy element production in neutron star mergers. The kilonova emission peaked at an absolute magnitude of -15.7 in the I band approximately 1.5 days after the merger. The total ejecta mass was estimated at 0.05 solar masses, with velocities ranging from 0.1 to 0.3 times the speed of light. The composition included approximately 0.01 solar masses of lanthanide elements, sufficient to explain the observed opacity and color evolution. Multi-wavelength observations of GW 170817 continued for months after the initial detection. X-ray emission was first detected 9 days post-merger with the Chandra X-ray Observatory, while radio emission became detectable after 16 days using the Carl G. Jansky Very Large Array. The late-time emission showed the characteristic behavior of an off-axis relativistic jet interacting with the surrounding environment. The discovery rate of gamma-ray bursts has increased dramatically with improved detection capabilities. The burst and transient source experiment aboard the Compton Gamma Ray Observatory detected 2,704 bursts between 1991 and 2000, establishing an all-sky rate of approximately 1 burst per day. The SWIFT mission has detected over 1,500 bursts since its launch in 2004, while Fermi has observed more than 3,000 events since beginning operations in 2008. The spatial distribution of detected gamma-ray bursts shows the expected isotropic pattern for cosmological sources, with no significant clustering toward the galactic plane or other structures. Statistical tests confirm isotropy at confidence levels exceeding 99.9%, providing strong evidence against galactic origin models that were proposed during the early years of gamma-ray burst research. The temporal distribution of gamma-ray bursts appears random on all timescales from milliseconds to years. Autocorrelation analyses show no evidence for periodicity or clustering in burst arrival times, consistent with expectations for explosions of individual stars in distant galaxies. The Poisson character of burst statistics has been verified through multiple statistical tests. Intensity variations within individual gamma-ray bursts can occur on timescales as short as milliseconds, providing constraints on the size of emission regions through light travel time arguments. The minimum variability timescale observed is approximately 0.1 milliseconds in GRB 910323, implying an emission region size smaller than 30 kilometers. This constraint supports models involving compact objects such as neutron stars or stellar mass black holes. The spectra of gamma-ray bursts typically exhibit non-thermal shapes that can be described by the band function, a smoothly broken power law with different photon indices below and above a characteristic energy. The low energy photon index typically ranges from negative 1.5 to 0, while the high energy index is usually between negative 2.5 and negative 1.5. The peak energy of the spectrum varies from a few kilo-electron volts to several mega-electron volts. Spectral evolution during gamma-ray bursts often shows a pattern of hard-to-soft evolution, where the peak energy decreases with time. This behavior is observed in approximately 70% of well-detected bursts and may reflect cooling of relativistic electrons in the emission region or evolution of the Lorentz factor in expanding relativistic flows. The polarization properties of gamma-ray bursts provide insights into magnetic field configurations and emission mechanisms. Linear polarization measurements have been attempted for several dozen bursts, with detections claimed for approximately 20% of the sample. The reported polarization fractions range from 10% to 80%, though systematic uncertainties remain large. The Icaros solar sail mission carried the gamma-ray burst analyzing polarimeter (GAP) instrument, which achieved polarization measurement precision of approximately 10% for bright bursts. The mission detected potential polarization signals from several events, but definitive measurements remain challenging due to the brief duration and limited statistics of gamma-ray burst observations. Circular polarization searches have been conducted for a smaller number of bright bursts, with upper limits typically ranging from 10% to 50%. The detection of circular polarization would provide unique insights into the role of magnetic fields and relativistic effects in burst emission regions. The afterglow emission from gamma-ray bursts extends across the entire electromagnetic spectrum from radio to X-rays. Optical afterglows have been detected for approximately 60% of well-localized swift bursts, with initial magnitudes ranging from 15 to 25 in standard broadband filters. The afterglow light curves typically follow power law declines with temporal indices between -0.5 and -2.5. Afterglow spectral energy distributions can be fit with synchrotron emission models involving power law distributions of relativistic electrons. The electron energy distribution typically has an index P approximately 2.2 to 2.8, consistent with expectations for particle acceleration in relativistic shocks. The magnetic field strength in afterglow emission regions is estimated at 1 to 100 Gauss. The external shock model for afterglow emission predicts specific relationships between temporal and spectral indices that depend on the density profile of the circumburst environment and the observing frequency relative to characteristic break frequencies. These relationships, known as closure relations, have been tested using multi-wavelength afterglow observations from hundreds of bursts. Approximately 30% of well-observed afterglow exhibit significant deviations from simple power law decay, including shallow decay phases, plateau emission, and late-time flares. These departures from the standard external shock model require additional energy injection from the central engine or complex circumburst environments. Prompt optical emission has been detected during the gamma ray phase for approximately 20 bursts, providing unique constraints on emission mechanisms and magnetic field configurations. The earliest optical detection was achieved 11 seconds after trigger for GRB 080319b using the Tortora wide field camera system. The prompt optical emission typically shows different temporal behavior from the gamma ray light curve, suggesting partially distinct emission mechanisms. The reverse shock component of gamma ray burst afterglows has been clearly identified in radio and millimeter observations of several events. This emission component peaks earlier than the forward shock and provides information about the initial Lorentz factor and magnetization of the relativistic ejecta. Reverse shock detections require very early observations, typically within hours of the burst. Superluminal motion has been detected in the radio afterglow of several gamma ray bursts through very long baseline interferometry observations. GRB 030329 showed apparent expansion velocities of 4.1 times the speed of light, while GRB 170817 exhibited apparent motion at 2.4 times light speed. These measurements provide direct confirmation of relativistic expansion and enable determination of jet opening angles. The jet opening angles of gamma ray bursts range from approximately 2 to 20 degrees, with a median value near 6 degrees. These measurements come from identifying jet break times in afterglow light curves when the relativistic beaming becomes less effective and the observed flux drops more rapidly. The narrow jet opening angles reduce the true energy requirements for gamma ray bursts by factors of 100 to 1000 compared to isotropic emission assumptions. The efficiency of converting kinetic energy to gamma ray emission in gamma ray bursts is typically 1 to 10%, based on comparisons between prompt gamma ray energy and inferred kinetic energy from afterglow modeling. This efficiency is comparable to that achieved in the most powerful astrophysical jets and approaches theoretical limits for electromagnetic energy extraction from rotating black holes. Neutrino searches associated with gamma ray bursts have been conducted using the ice cube detector in Antarctica, which monitors a cubic kilometer of ice for Cherenkov radiation from high-energy neutrino interactions. Despite searching coincidences with over 300 gamma ray bursts detected between 2008 and 2018, no significant neutrino associations have been confirmed. The upper limits on neutrino fluence from gamma ray bursts constrain the fraction of explosion energy carried by relativistic protons. For typical burst parameters, the limits suggest that either gamma ray burst jets are dominated by electron-positron pairs rather than protons, or that hadronic acceleration is less efficient than some theoretical models predict. The search for ultra-high energy cosmic rays from gamma ray bursts has been conducted using the Pierre Auger Observatory in Argentina and the Telescope Array in Utah. These facilities detect extensive air showers produced when cosmic rays with energies exceeding 10 to the 18th electron volts interact with Earth's atmosphere. No significant correlations have been found between cosmic ray arrival directions and known gamma-ray burst positions. The time delay searches for ultra-high energy cosmic rays from gamma-ray bursts account for deflection by intergalactic magnetic fields and energy loss interactions with cosmic microwave background photons. For bursts at redshift Z approximately 1, the expected arrival time delays range from years to decades, depending on particle energy and magnetic field assumptions. Magnetic field measurements in gamma-ray burst environments have been achieved through Faraday rotation studies of polarized afterglow emission. The rotation measure values typically range from 10 to 1,000 radians per square meter, implying magnetic field strengths of 0.01 to 1 Gauss in the host galaxy interstellar medium along the line of sight. The circumburst density estimates from afterglow modeling range from 0.1 to 1,000 particles per cubic centimeter, with a median value near 1 particle per cubic centimeter. These densities are comparable to typical values in galactic star-forming regions and support the association of long-duration bursts with massive star progenitors. Wind-like density profiles, where density decreases as the inverse square of distance from the progenitor star, have been inferred for approximately 25% of well-studied afterglows. These profiles are consistent with mass loss from Wolf-Rayet stars or luminous blue variables during their final evolutionary phases. The metallicity measurements in gamma-ray burst host galaxies employ emission line ratios observed in optical spectra. The most commonly used diagnostic is the R23 parameter, defined as the ratio of O2A lambda 3727 plus O3 lambda lambda 4959 5007 to H beta emission line fluxes. This ratio correlates with oxygen abundance, but requires additional diagnostics to break degeneracies. Alternative metallicity indicators include the N2 parameter, N2 lambda, 6584 H alpha, and the O3 N2 diagnostic, O3 lambda, 5007 H beta, N2 lambda, 6584 H alpha. These indicators show consistent results, indicating that gamma-ray burst host galaxies are typically metal poor compared to the general star-forming galaxy population at similar redshifts. The star formation rates in gamma-ray burst host galaxies range from 0.01 to 100 solar masses per year, with a median value of approximately 1 solar mass per year. These rates are derived from emission line luminosities, ultraviolet continuum fluxes, and infrared measurements that trace ongoing star formation activity. The specific star formation rates, star formation rate per unit stellar mass, in gamma-ray burst hosts are typically elevated compared to field galaxies at similar redshifts. The median specific star formation rate is approximately 10 to the -9th per year, indicating that burst hosts are actively forming stars relative to their existing stellar populations. Dust extinction measurements in gamma-ray burst host galaxies show a wide range from negligible reddening to visual extinctions exceeding 5 magnitudes. The extinction follows a power law distribution, with most galaxies showing modest dust content. The dust properties often differ from those in the Milky Way, with flatter extinction curves and different ratios of total to selective extinction. The morphological classification of gamma-ray burst host galaxies based on Hubble Space Telescope imaging shows a high fraction of irregular and peculiar systems. Approximately 45% are classified as irregular, 25% as spiral galaxies, 20% as compact objects without clear structure, and 10% as elliptical or early-type galaxies. The size distribution of gamma-ray burst host galaxies shows effective radii ranging from 0.5 to 10 kiloparsecs, with a median value of approximately 2.5 kiloparsecs. These sizes are smaller than typical star-forming galaxies at similar redshifts, consistent with the preference for low-mass, compact hosts. Surface brightness measurements of gamma-ray burst host galaxies reveal both high and low surface brightness systems. The central surface brightness in the rest frame B band ranges from 18 to 25 magnitudes per square arc second, with some hosts falling below traditional survey detection limits. The velocity dispersion measurements in gamma-ray burst host galaxies, obtained from emission line widths, typically range from 20 to 100 kilometers per second. These values correspond to dynamical masses of 10 to the power of 8 to 10 to the power of 10 solar masses, consistent with stellar mass estimates from spectral energy distribution fitting. Chemical abundance gradients within gamma-ray burst host galaxies have been measured for approximately 20 systems using integral field spectroscopy. The gradients are typically shallow, with metallicity decreasing by 0.1 to 0.3 dex per scale length, similar to local star-forming galaxies, but flatter than typical spiral galaxies. The age distributions of stellar populations in gamma-ray burst host galaxies show evidence for recent star formation activity. Population synthesis modeling indicates that 10 to 50% of the stellar mass formed within the past 100 million years, much higher than typical field galaxies. Supernova searches in gamma-ray burst host galaxies have revealed rates 2 to 5 times higher than expected based on current star formation rates. This enhancement may indicate that gamma-ray burst progenitors are associated with particularly active star formation episodes or regions. The clustering properties of gamma-ray burst host galaxies have been studied using large-scale structure measurements. The correlation function indicates that burst hosts reside in dark matter halos with typical masses of 10 to the 11th to 10 to the 12th solar masses, similar to the halos hosting Lyman break galaxies at comparable redshifts. Environment studies around gamma-ray burst host galaxies show that approximately 30% have close companions within 50 kiloparsecs and velocity differences less than 500 kilometers per second. This companion fraction is similar to field galaxies at comparable redshifts, suggesting that galaxy interactions do not strongly influence gamma-ray burst production. The redshift evolution of gamma-ray burst host galaxy properties shows systematic changes with cosmic time. Higher redshift hosts tend to be smaller, less massive, more actively star-forming, and more metal-poor than lower redshift systems. These trends mirror the general evolution of the star-forming galaxy population. Quasar absorption line studies along gamma-ray burst sightlines have provided unique probes of intergalactic medium properties. The intervening absorber statistics are consistent with those found along quasar sightlines, but the much more precise localizations of gamma-ray bursts enable detailed studies of individual absorption systems. The damped Lyman alpha systems detected in gamma-ray burst afterglow spectra typically show neutral hydrogen column densities exceeding 10 to the 20 atoms per square centimeter. These systems are associated with galactic disks or halos and provide information about the gas content of galaxies not directly detectable in emission. Metal line absorption studies in gamma-ray burst spectra have revealed detailed chemical abundance patterns in high redshift galaxies. The relative abundances of elements like silicon, iron, zinc, and chromium provide constraints on star formation histories and supernova enrichment processes in early galactic systems. Fine structure line absorption in gamma-ray burst spectra probes the physical conditions in intervening gas clouds. The excited states of carbon and silicon ions are sensitive to local ultraviolet radiation fields and gas densities, providing information about star formation activity in absorbing galaxies. The cosmic microwave background temperature measurements using gamma-ray burst absorption lines have provided tests of standard cosmological models. The excited fine structure levels of carbon and oxygen ions are sensitive to the ambient radiation temperature, which should increase with redshift as T equals T0 times 1 plus Z to the power of 1 plus Z in standard cosmology. Gravitational lensing effects have been detected for approximately 10 gamma-ray bursts, where foreground galaxies or galaxy clusters magnify and distort the burst images. The most dramatic case is GRB 090323, which showed evidence for multiple images with different arrival times separated by several seconds. Weak lensing studies using large samples of gamma-ray burst positions have constrained the matter distribution along random lines of sight through the universe. The statistical analysis of image distortions provides independent measurements of cosmological parameters, including the matter density and dark energy equation of state. The time dilation effects predicted by cosmological expansion have been detected in gamma-ray burst light curves through statistical studies of pulse widths and variability timescales. Bursts at higher redshifts show systematically longer durations and lower variability frequencies, consistent with special relativistic time dilation. Luminosity function studies of gamma-ray bursts suggest that the local rate density is approximately 1 burst per 10 to the 6th solar masses of stellar mass formed, corresponding to roughly 1 burst per 10 to the power of 5 massive stars. This rate is consistent with theoretical models where gamma-ray bursts represent a rare outcome of massive star evolution. The beaming corrected rates of gamma-ray bursts are approximately 100 times higher than the observed rates, accounting for the narrow jet opening angles. The true rate of core collapse events producing relativistic jets may be as high as 1% of all massive star deaths. Energy budget calculations for gamma-ray burst populations suggest they contribute approximately 10 to the 51st ergs per cubic megaparsec per year to the cosmic explosion energy density. This energy input is comparable to supernova contributions and may influence the chemical and thermal evolution of the intergalactic medium. The contribution of gamma-ray bursts to cosmic ionization depends on their rate evolution at high redshifts and the escape fraction of ionizing photons from their host galaxies. Current estimates suggest that bursts may contribute 1 to 10% of the ionizing background at redshifts Z greater than 6, playing a secondary role compared to early galaxies and quasars. Heavy element production in gamma-ray burst jets through ER process nucleosynthesis may contribute significantly to cosmic chemical evolution. The rapid neutron capture process can occur in neutron-rich ejecta from collapsing massive stars or neutron star mergers, producing elements heavier than iron. The total mass of R-process elements produced per gamma-ray burst ranges from 10 to the -5 to 10 to the -2 solar masses, depending on the progenitor model and explosion mechanism. When integrated over cosmic time, this production may account for a significant fraction of the heavy elements observed in the universe today. The magnetic field amplification mechanisms operating in gamma-ray burst shocks have been studied through plasma simulations and observational constraints. The field strengths required for efficient particle acceleration exceed those in the ambient medium by factors of 100 to 1000, requiring in situ generation through plasma instabilities. Weibel instabilities in counterstreaming plasma flows can generate magnetic fields on short timescales through the growth of current filaments. These instabilities operate efficiently in relativistic shocks and can produce field strengths approaching equipartition with the kinetic energy density. The particle acceleration efficiency in gamma-ray burst shocks approaches the theoretical maximum for first-order Fermi acceleration in strong shocks. Approximately 10 to 20% of the shock energy can be transferred to a power law distribution of relativistic electrons, with spectral indices consistent with afterglow observations. The maximum particle energies achievable in gamma-ray burst shocks are limited by synchrotron cooling and shock geometry. For typical burst parameters, electrons can be accelerated to Lorentz factors exceeding 10 to the 6th power, while protons may reach energies of 10 to the 20th power electron volts under favorable conditions. Quantum electrodynamic effects in the extreme magnetic fields near gamma-ray burst sources may modify photon propagation and pair production processes. Magnetic field strengths approaching the critical value of 4.4 times 10 to the power of 13, Gauss can induce vacuum birefringence and photon splitting phenomena. The compactness problem in gamma-ray burst emission involves the apparent conflict between high gamma-ray luminosities and the transparency requirements for photon escape. The problem is resolved through relativistic motion that reduces the optical depth for pair production in the source rest frame. Lorentz factors of gamma-ray burst ejecta are constrained by opacity arguments and afterglow observations to range from 100 to 1000. These extreme velocities approach the theoretical limits for energy extraction from rotating black holes or neutron stars through magnetic field interactions. The collimation mechanisms for gamma-ray burst jets involve complex magnetohydrodynamic processes in the vicinity of rotating compact objects. The jet opening angles are determined by the balance between magnetic pressure and gas pressure in the acceleration region. Numerical simulations of gamma-ray burst jet formation require three-dimensional magnetohydrodynamic codes with relativistic equation of state and neutrino transport. The computational demands exceed current capabilities for self-consistent modeling from stellar core collapse through jet propagation and gamma-ray production. The progenitor mass range for long-duration gamma-ray bursts is constrained by stellar evolution models and supernova associations. The minimum mass appears to be approximately 25 solar masses, while the maximum may exceed 100 solar masses for population 3 stars in the early universe. Rotation rate requirements for gamma-ray burst progenitors approach the breakup limit for massive stars. The specific angular momentum must be maintained during stellar evolution despite mass loss and magnetic braking, requiring special circumstances or binary interactions. The metallicity threshold for efficient gamma-ray burst production appears to be approximately 0.3 times solar abundance, below which stellar winds become ineffective at removing the hydrogen envelope. This threshold explains the preference for low metallicity host galaxies observed in burst samples. Binary evolution scenarios for gamma-ray burst progenitors involve complex mass transfer phases that can spin up stellar cores while stripping outer layers. The final helium star masses range from 4 to 15 solar masses, depending on the initial binary parameters and evolution history. The delay time distribution between star formation and gamma-ray burst explosion shows a characteristic timescale of 30 to 100 million years for the bulk of the population, with a tail extending to several billion years. This distribution reflects the main sequence lifetimes of massive stars and possible delays in binary evolution. Population synthesis models predict gamma-ray burst rates that depend sensitively on the initial mass function, binary fraction, and metallicity evolution of stellar populations. The models generally reproduce observed rates within factors of 2 to 3, but significant uncertainties remain in the input physics. The black hole mass distribution for gamma-ray burst progenitors, inferred from supernova observations and stellar evolution models, typically ranges from 5 to 50 solar masses. The mass correlates with the progenitor stellar mass and affects the properties of accretion disks and jet formation. Accretion disk physics in gamma-ray burst central engines involves neutrino cooling, magnetic field amplification, and relativistic effects near the black hole event horizon. The disk lifetime of 10 to 100 seconds determines the duration of energy injection into the relativistic jet. The Blandford-Zanojek mechanism for energy extraction from rotating black holes provides a natural explanation for gamma-ray burst jet power. The mechanism can extract up to 29% of the black hole rest mass energy for maximally rotating Kerr black holes. Magnetar formation scenarios for gamma-ray burst central engines require neutron stars with magnetic field strengths exceeding 10 to the 15th Gauss and rotation periods of 1 to 10 milliseconds. The magnetic dipole radiation and magnetospheric processes can power jets for timescales comparable to observed burst durations. The equation of state for neutron star matter affects the maximum mass that can be supported against gravitational collapse. Recent neutron star mass measurements suggest maximum masses near 2.0 to 2.5 solar masses, constraining the stiffness of the nuclear equation of state. Neutrino emission from gamma-ray burst central engines carries away most of the gravitational binding energy released during core collapse. The neutrino luminosity can exceed 10 to the 53rd ergs per second for timescales of 10 to 100 seconds, providing the energy reservoir for relativistic jet formation. The temporal structure of gamma-ray burst light curves reflects the complex interplay between central engine activity, jet propagation, and shock interactions. The observed variability timescales range from milliseconds to hundreds of seconds, providing constraints on emission mechanisms and source geometry. Statistical studies of gamma-ray burst temporal properties have revealed correlations between pulse width, intensity, and spectral hardness. These relationships, known as pulse intensity correlations, provide insights into the emission physics and may enable burst classification schemes. The lag luminosity relationship for gamma-ray bursts describes the correlation between spectral lag, time delay between high and low energy photons, and peak luminosity. This relationship has been proposed as a distance indicator for cosmological applications, analogous to the Tully-Fisher relation for galaxies. However, the physical origin of the lag-luminosity relationship remains unclear, and its applicability as a standard candle is limited by large scatter and potential evolution effects. Alternative correlations involving burst duration and spectral parameters may provide more robust distance indicators. The Amati relation connects the peak energy in burst spectra with the total isotropic energy release. This correlation extends over several orders of magnitude and may reflect fundamental aspects of the emission mechanism, but it also shows significant scatter that limits cosmological applications. The search for standard candle relationships in gamma-ray bursts continues through studies of larger samples with improved distance measurements. The goal is to develop gamma-ray burst cosmology as a complement to supernova and cosmic microwave background studies of cosmic expansion. Systematic uncertainties in gamma-ray burst cosmology include selection effects, host galaxy extinction, instrumental calibration, and theoretical modeling assumptions. These uncertainties currently limit the precision of cosmological parameter measurements to levels comparable to other techniques. Future gamma-ray burst missions will address these systematic uncertainties through improved sensitivity, better localization capabilities, and broader energy coverage. The enhanced data quality will enable more precise tests of cosmological models and fundamental physics. The technological requirements for next-generation gamma-ray burst detectors include large collecting areas, wide fields of view, high temporal resolution, and autonomous rapid response capabilities. These requirements push the boundaries of current spacecraft and detector technologies. Proposed mission concepts include constellation approaches with multiple smaller satellites, large area coded aperture instruments, and focusing telescopes for high-energy gamma rays. Each approach offers different advantages for specific science objectives while facing distinct technical challenges. The international coordination of future gamma-ray burst missions will be essential for maintaining continuous sky coverage and enabling rapid multi-wavelength follow-up observations. The coordination requires agreements on data sharing, alert distribution, and observational priorities. Educational and outreach applications of gamma-ray burst research continue to evolve with advancing technology and increasing public interest in cosmic explosions. Virtual reality environments, interactive simulations, and citizen science projects provide new ways to engage diverse audiences with cutting-edge astronomical research. The cultural legacy of gamma-ray burst research extends beyond immediate scientific discoveries to include technological innovations, international collaborations, and inspirational impacts on human understanding of the universe. The field exemplifies humanity's capacity to decode cosmic messages and expand our comprehension of natural phenomena operating under the most extreme conditions imaginable. The signals from these cosmic catastrophes continue their multi-billion-year journeys across space, carrying information about stellar death, black hole formation, and the fundamental limits of physics under extreme conditions. Each detection represents a successful interception of these ancient messages, adding new pieces to our understanding of cosmic evolution and the magnificent violence that shapes the universe on its largest scales. The computational infrastructure required for modern gamma-ray burst research represents one of the most sophisticated data processing systems ever developed for astronomical applications. The Fermi Gamma-Ray Space Telescope alone generates approximately 8 gigabytes of science data daily, requiring real-time analysis algorithms capable of identifying potential burst candidates within seconds of detection. The spacecraft's onboard computers employ field-programmable gate arrays running at 40 MHz to perform initial event filtering and classification. Ground-based processing systems for gamma-ray burst data operate at the Fermi Science Support Center at NASA Goddard Space Flight Center, where a cluster of 200 computer nodes provides 2.4 teraflops of computational power. The automated analysis pipeline can process a full day's worth of Fermi data in approximately 4 hours, searching through millions of potential event combinations to identify genuine cosmic explosions among the background of particle hits and instrumental artifacts. The false positive rejection algorithms employed in gamma-ray burst detection represent sophisticated applications of pattern recognition and machine learning techniques. The Fermi Gamma-Ray Burst Monitor processes approximately 50,000 triggered events daily, of which only 2 to 3 prove to be genuine cosmic gamma-ray bursts. The remaining triggers result from solar particle events, terrestrial gamma-ray flashes, cosmic ray interactions, and various instrumental effects. Machine learning classifiers trained on decades of gamma-ray burst data can distinguish genuine events from false alarms, with accuracy rates exceeding 99.8%. These algorithms analyze dozens of parameters, including trigger duration, spectral hardness, spatial distribution across detectors, and temporal structure. The most sophisticated systems employ deep neural networks with multiple hidden layers trained on datasets containing over 100,000 labeled examples. The Rapid Alert Distribution System for Gamma-Ray Burst Discoveries operates through the Gamma-Ray Coordinates Network, which maintains connections to over 300 observatories worldwide. When a burst is detected and verified, automated alerts are transmitted via internet, telephone, and satellite communication links within an average time of 12 seconds. The alert messages contain burst coordinates accurate to 1 to 3 degrees, enabling ground-based telescopes to begin follow-up observations within minutes. The international coordination required for gamma-ray burst follow-up observations operates across 24 time zones and involves researchers speaking over 20 different languages. Real-time communication occurs through dedicated chat channels, email lists, and automated notification systems that ensure critical information reaches the appropriate observers regardless of local time. The linguistic challenges have led to the development of standardized terminology and automated translation systems for essential observational information. Weather monitoring systems at major observatories provide real-time information about observing conditions that affect gamma-ray burst follow-up priorities. Automated weather stations measure cloud cover, atmospheric transparency, humidity, and wind conditions at 5-minute intervals. This information is integrated into scheduling algorithms that optimize telescope assignments based on both astronomical priorities and local observing conditions. The economic cost of gamma-ray burst research extends far beyond the initial spacecraft development to include decades of operational expenses, data analysis, and follow-up observations. NASA's total investment in the Fermi mission approaches $1.2 billion when including development, launch, and 15 years of operations. The European Space Agency's contribution to gamma-ray burst research through the Integral mission represents an additional €600 million investment. Ground-based follow-up observations for gamma-ray bursts consume approximately 500 telescope nights annually across all major observatories worldwide. At current operational costs of $50,000 to $100,000 per night for 8 to 10 meter-class telescopes, the annual expenditure for gamma-ray burst follow-up exceeds $40 million. These costs include telescope operations, instrumentation development, and data processing infrastructure. The human resources dedicated to gamma-ray burst research encompass approximately 2,000 scientists and engineers worldwide, including 800 graduate students and postdoctoral researchers. The field supports academic programs at over 150 universities across 40 countries, with specialized training programs in high-energy astrophysics, space instrumentation, and rapid response observational techniques. Career development in gamma-ray burst research requires mastery of diverse technical skills, including spacecraft operations, detector physics, data analysis programming, statistical methods, and multi-wavelength observational techniques. Graduate students typically spend 2 to 3 years learning these skills before contributing to original research, while postdoctoral positions often involve 3 to 5 year commitments to specific missions or observational programs. The interdisciplinary nature of gamma-ray burst research creates unique collaborative opportunities between traditional astronomy departments and physics, engineering, and computer science programs. Many universities have established joint degree programs that combine astronomical training with specialized technical skills needed for space-based research. These programs often include internships at NASA centers, European Space Agency facilities, or aerospace companies. Gender representation in gamma-ray burst research has improved significantly over the past 2 decades, with women comprising approximately 35% of graduate students and 28% of postdoctoral researchers in the field. However, representation decreases at higher career levels, with women holding only 18% of tenured faculty positions in gamma-ray burst research groups. Professional organizations have implemented mentorship programs and family-friendly policies to address these disparities. International exchange programs, facilitated by gamma-ray burst collaborations, have enabled over 1,500 students and researchers to spend extended periods at institutions in different countries. These exchanges often last 6 to 12 months and provide exposure to different research techniques, cultural perspectives, and scientific approaches. The long-term relationships formed through these programs have strengthened international collaboration and understanding. The technological spin-offs from gamma-ray burst research have generated over 150 patent applications covering detector technologies, signal processing algorithms, and data analysis methods. Commercial applications include medical imaging systems, nuclear security scanners, space weather monitoring, and telecommunications signal processing. Several startup companies founded by gamma-ray burst researchers have achieved valuations exceeding $100 million. Medical imaging applications of gamma-ray burst detector technology have improved the sensitivity and speed of positron emission tomography scanners used in cancer diagnosis and treatment monitoring. The timing resolution achieved in gamma-ray burst detectors, measured in nanoseconds, enables more precise localization of radioactive tracers within the human body. These improvements have reduced scan times and radiation exposure for patients. Nuclear security applications employ gamma-ray detection techniques originally developed for astronomical research to identify radioactive materials in shipping containers, vehicles, and cargo. The ability to distinguish different isotopes based on their gamma-ray signatures has enhanced border security and nuclear non-proliferation efforts. Commercial systems based on astronomical detector technology can identify threat materials with false alarm rates below 0.1%. Space weather monitoring benefits from gamma-ray burst research through improved understanding of solar particle events and their effects on satellite systems. The same detectors that search for cosmic explosions also monitor solar flares and coronal mass ejections that can damage spacecraft electronics and disrupt communication systems. Real-time space weather alerts protect billions of dollars worth of satellite infrastructure. The data storage requirements for gamma-ray burst archives have grown exponentially with improving detector sensitivity and temporal resolution. The complete archive of Fermi observations contains over 15 years of continuous data totaling approximately 40 terabytes. Long-term preservation requires migration to new storage media every 5 to 7 years to prevent data loss from obsolete formats or degraded storage systems. Cloud computing platforms have revolutionized gamma-ray burst data analysis by providing scalable computational resources accessible to researchers worldwide. Amazon Web Services, Google Cloud Platform, and Microsoft Azure all host astronomical data analysis environments that enable researchers without access to large computing facilities to perform sophisticated analyses. These platforms have democratized access to cutting-edge computational tools. The development of specialized software packages for gamma-ray burst analysis has created an ecosystem of open-source tools used by researchers globally. The Fermi Science Tools, developed by NASA, provide standardized analysis capabilities for gamma-ray data and have been downloaded over 50,000 times. Similar software packages exist for Swift, Integral, and other missions, enabling consistent analysis approaches across different data sets. Version control systems originally developed for software engineering have been adapted for collaborative gamma-ray burst research. Platforms like GitHub and GitLab host repositories containing analysis code, documentation, and research results that can be shared among international collaborations. These systems track changes and contributions from dozens of researchers working on complex analysis projects. The peer review process for gamma-ray burst research has evolved to accommodate the rapid pace of discovery and the need for quick publication of time-critical results. Specialized journals maintain expedited review tracks for gamma-ray burst discoveries, with typical review times of 2 to 4 weeks compared to 3 to 6 months for regular submissions. Electronic submission and review systems enable faster communication between authors, reviewers, and editors. Preprint servers have become essential tools for rapid dissemination of gamma-ray burst research results. The Arcs of Preprint repository receives approximately 200 gamma-ray burst papers annually, allowing researchers to share results immediately while formal peer review proceeds. Many important discoveries are first announced through preprints, enabling rapid follow-up observations and theoretical modeling. Social media platforms have transformed how gamma-ray burst discoveries are communicated to both scientific and public audiences. Twitter feeds from major missions and research groups provide real-time updates on new detections, while Facebook pages and YouTube channels offer educational content about cosmic explosions. These platforms reach millions of people worldwide and generate public interest in astronomical research. The visualization techniques developed for gamma-ray burst data have advanced significantly with improvements in computer graphics and virtual reality technology. Three-dimensional models of burst jets and shock interactions help researchers understand complex physical processes, while immersive virtual reality environments enable exploration of cosmic explosion simulations. Artificial intelligence applications now extend beyond detection algorithm. The visualization techniques developed for gamma-ray burst data have advanced significantly with improvements in computer graphics and virtual reality technology. Three-dimensional models of burst jets and shock interactions help researchers understand complex physical processes, while immersive virtual reality environments enable exploration of cosmic explosion simulations. Artificial intelligence applications now extend beyond detection algorithms to include automated classification of burst properties, prediction of optimal follow-up strategies, and natural language processing of the vast research literature to identify patterns invisible to human readers. The standardization of data formats across different missions has enabled powerful meta-analyses combining decades of observations, revealing subtle correlations and population properties that require large samples spanning multiple spacecraft. Quality control procedures ensure observational records remain accurate and accessible, with automated checks verifying data integrity while expert astronomers identify potential calibration problems. These quality assurance measures prevent error propagation that could affect conclusions from large statistical studies. International agreements governing gamma-ray burst research address data sharing policies, publication protocols, intellectual property rights, and export control regulations. These complex arrangements must accommodate different national priorities and legal frameworks while enabling effective scientific collaboration. Mission operators require specialized training in spacecraft systems, detector physics, and rapid response procedures, preparing them to handle anomalies and unexpected events on timescales of minutes to hours through simulator exercises and emergency response drills. The technology transfer mechanisms from gamma-ray burst research have generated over 150 patent applications covering detector designs, signal processing algorithms, and data analysis techniques. Commercial applications include medical imaging systems with nanosecond timing precision, nuclear security scanners achieving false alarm rates below 0.1%, and space weather monitoring protecting billions of dollars in satellite infrastructure. Venture capital investment in startups founded by gamma-ray burst researchers has created companies with valuations exceeding $100 million. Educational outreach programs serve over 10 million people annually through planetarium shows, museum exhibits, and citizen science projects translated into more than 30 languages. NASA's Fermi mission website receives over 500,000 unique visitors annually, while mission social media accounts have accumulated more than 2 million followers. The cultural impact extends beyond science to inspire visual artists, musicians, and science fiction authors exploring themes of cosmic violence and stellar death. Environmental stewardship at observatories includes carbon footprint reduction, renewable energy installations, and ecosystem monitoring in protected areas around facilities. Many observatories partner with indigenous communities on lands with cultural significance, creating opportunities for educational collaboration while respecting traditional knowledge. The economic impact often exceeds direct employment, with observatory tourism attracting hundreds of thousands of visitors annually. The future sustainability of gamma-ray burst research depends on maintaining continuous sky coverage as older missions reach end of life, balancing costs of new capabilities with preserving existing observational abilities. Commercial space industry involvement has expanded dramatically as launch costs decrease and small satellite capabilities improve. CubeSat missions now cost 100 to 1,000 times less than traditional spacecraft, while providing valuable scientific capabilities, democratizing access to space for university programs and smaller institutions. Next-generation detector technologies under development include cryogenic microcalorimeters with energy resolution approaching 1 electron volt, position-sensitive detectors with spatial resolution below 100 micrometers, and timing systems with precision better than 10 nanoseconds. Space-based interferometry concepts would employ multiple spacecraft flying in formation to achieve angular resolution comparable to ground-based optical interferometers, potentially enabling direct imaging of gamma-ray burst emission regions. The search for neutrino astronomy facilities are being designed specifically to detect predicted signals from gamma-ray bursts, with the proposed IceCube Gen 2 detector instrumenting 8 cubic kilometers of Antarctic ice for 8 times greater sensitivity than current capabilities. Next-generation gravitational wave detectors like Cosmic Explorer and Einstein Telescope will achieve strain sensitivities 10 times better than current systems, potentially observing hundreds of merger-associated gamma-ray bursts annually from throughout the observable universe. The precision timing capabilities of gamma-ray burst observations enable tests of general relativity and fundamental constants over cosmological distances. Time delays between photons of different energies could reveal violations of Lorentz invariance, while spectroscopic observations of absorption lines in afterglows constrain variations in the fine structure constant with precision comparable to laboratory measurements but over much longer timescales. Laboratory astrophysics experiments employ powerful laser systems like the National Ignition Facility's 192 focused beams to create conditions similar to relativistic shocks, testing theoretical predictions about particle acceleration and magnetic field generation. Plasma physics simulations require supercomputers with thousands of processor cores running for months to model jet formation and evolution across many orders of magnitude in spatial and temporal scales. The theoretical modeling of gamma-ray burst central engines has advanced through improved understanding of black hole physics and relativistic plasma processes, though current models struggle with the most extreme events that challenge stellar physics limits. Alternative energy sources, including primordial black hole evaporation and cosmic string interactions, have been proposed for events exceeding what stellar collapse can reasonably produce. Cosmological applications continue developing as larger samples enable gamma-ray bursts to serve as standard candles for measuring cosmic expansion at redshifts where supernovae become too faint. Dark energy constraints from burst observations could complement existing measurements, though the complexity of burst physics introduces systematic uncertainties requiring careful understanding. The diversity and inclusion initiatives address historical underrepresentation through targeted recruitment, mentorship networks, and family-friendly policies, with women comprising approximately 35% of graduate students, but decreasing representation at higher career levels. International exchange programs have enabled over 1,500 researchers to spend extended periods at institutions in different countries, creating lasting partnerships that strengthen collaboration and cultural understanding. The technological trends driving future research include improved detector materials, advanced signal processing, artificial intelligence applications, and miniaturized spacecraft systems. The evolving space exploration landscape creates new opportunities through partnerships with commercial companies, international agencies, and private foundations, diversifying funding sources while enabling more ambitious missions. The cultural legacy encompasses technological innovations, international partnerships, educational programs, and inspirational contributions to human understanding of the universe. The field demonstrates humanity's capacity to decode cosmic messages and expand comprehension of natural phenomena operating under the most extreme conditions imaginable. The ongoing dialogue between humanity and the cosmos continues through each detection, adding new voices to our understanding of stellar death, black hole formation, and the fundamental physics governing cosmic evolution. Somewhere in the depths of space, another massive star approaches its final moments, perhaps destined to produce a gamma-ray burst that will challenge theoretical understanding and reveal new aspects of cosmic physics. The explosion will join the growing catalog of cosmic catastrophes that have transformed our understanding while inspiring continued exploration of the magnificent and terrifying processes operating at the extremes of physical possibility.